doesn't work this time. Okay, cool, thanks. Okay, thanks. Okay. Okay, shall we get started? Is it time? Okay. Okay, thanks, Mayank. Yeah, welcome to lecture 3. We've covered a lot in the last 2 lectures. Today I'm going to give maybe the last overview of the challenges and opportunities in memory systems. And then we're going to jump into a more detailed coverage of memory-centric computing. Does that sound good? Yeah? Okay, cool. Okay, just to give jog your memory, we were discussing, I was giving you several examples of how modern systems are bottlenecked by data storage and movement. And we were discussing why is memory so important, especially today. And we were giving different perspectives. We covered the performance, energy perspectives. You'll see a lot more as you read papers and as we actually go through lectures. Today, we're going to talk a little bit about scaling and robustness and a little bit more perspectives. This is, again, just to jog your memory. Remember this picture that I showed you and took the perspective of a 10-year-old kid? If you actually have this thing designed and most of the resources you're dedicating for it are actually resources for memory and storage, intuitively, you would think that that's not your bottleneck, right? That should not be your bottleneck. But it turns out this is still your bottleneck. And the system is still not doing well. Yeah, I think we should be more like 10-year-old kids going into the future. I also think we should treat our 10-year-old kids very nicely because they are the future and they can critically think about how people design the systems. I had a very terrible experience today watching a tram driver ignoring a 10-year-old kid. Tram driver was sitting in the Bellevue station for 30 seconds. And this 10-year-old kid was trying to get into the tram, and he didn't open the door. I think we should pause and think, is this kindness? Or is this something else? Okay, I'll let you think about that, but I have very strong opinions on this. I think if your tram is waiting there for 30 seconds, nowhere to move, you should be opening that door. That's your duty to the public. Does that make sense? This is not the first time I'm experiencing it. This is the nth time I'm experiencing it. A tram should not come to the station and then immediately flash that yellow thing and then go away after waiting for 35, 40 seconds after flashing that thing and admitting no one was sitting over there. This is not human, in my opinion. And I think, especially done to a 10-year-old kid, it gives a very bad message, right? This is how you live. Okay, I digressed, but I think this is what I experienced with a 10-year-old kid today. I have evidence of this also on my phone, by the way. It's good to have evidence sometimes. Okay, so it's good to think about that. I think, what are we preparing the world for going into the future? As I said, we're going to question a lot of things in this course, and I'm not going to limit it to just the computing systems, frankly. As you can see, there's a world that we live in. There's an architecture that's built in that world. Is that the architecture we want? Right. It's good to think about that. And I think this is not the architecture we want going into the future. That's why we're going to look a lot into memory-centric computing. I think a lot of things are connected in the world. They're not separate because the mindset affects a lot of things. Okay, so you saw the slide before. We were discussing major trends affecting main memory. We discussed the first one. I'm not going to go through that again. The first one is about performance, essentially. Performance has many aspects: capacity, bandwidth, quality of service. Predictability is part of performance also. If you think about it, if you stretch it, it's also part of robustness. It's essentially part of goals. And then we talked about energy and power. That was also very important. And I gave you a bunch of data and pictures showing that data movement energy, it really dominates compute energy. And maybe we should be thinking how to amortize that energy cost in a much better way. And today, amortizing that energy cost by exploiting locality in caches is very difficult. So if we actually have techniques that enable computation capability somewhere else, you can maybe not even incur that energy cost of moving data, or you move data very little inside the memory system to do computation. And we're going to talk about that. And I've gone through this, so I'm not going to go through it again right now. We're going to see more of this. At least, hopefully we'll start it today, we'll see, or we'll start it tomorrow. Okay, and I've already given you prefetched a bunch of papers that you might be reading during this course. Okay, this is where we were. Actually, this is not exactly where we were, but this is the general area that we were kind of in the middle of. We were discussing technology scaling, and technology scaling has enabled a lot of benefits in terms of increasing capacity, lowering costs, lowering energy, maybe even helping with latency. That's debatable, but it's not, at least not in DRAM, because you're dominated by interconnects in DRAM, and reducing the size of the cell doesn't help your latency as much. In fact, it may hurt your latency, because as you reduce the size of your cell, it turns out you have very little charge, and you have very little charge that perturbs the bit lines. Okay, but basically, as you reduce the size of the cell, you get some benefits. And if your downsides outweigh your benefits, it's always good to ask the question, do I want to scale my technology going into the future? That's true with any technology, right? It's actually good to think about that from the LLM perspective also. If our downsides outweigh our benefits, should we really be trying to scale these LLMs, or should we be looking at other technologies, right? So it's good to think about that. Now our focus is on memory, DRAM especially. And as we scale this technology to smaller and smaller and smaller nanometers, it becomes problematic in multiple ways, especially robustness, as we have started discussing. And this is a picture that I showed you last time. Again, very quickly, DRAM is a very special technology. It's very dense. It consists of a capacitor storing charge. It consists of an access transistor that's enabling capacitor to communicate that charge with sensing structures, which include the bit line and the sense amplifier over here. We're going to see more of that later in the lecture today. But this is essentially your cell, which is very dense. And you can make the capacitor and access transistor smaller and smaller and smaller. And as you make them smaller, you can put more bits per millimeter square. And that enables you to scale to very large capacities, okay? So that sounds good. The problem is, as you reduce the size of these structures, it becomes difficult to sense the charge, reliable sensing. And it also becomes difficult to retain the charge, because you have very few electrons, if you will, in that capacitor. It's easy for them to escape. And there's another aspect of scaling, which is not just the size reduction, but it's also density increase, meaning the distances reduce as you scale, right? 10 nanometer becomes 5 nanometers, right? Clearly, the size of the structure is reduced, but the distances between different structures also reduce. The distance between this cell and some other cell, which is not shown here, but let's say next to it, also reduces. And as that reduces, these cells start affecting each other, because there's capacitive coupling, and there are different types of noise that impact. Whenever you access one cell, you're inducing some electromagnetic noise in adjacent cells. It's good to think about it that way. I think of it as electromagnetic noise in the end. So basically, when you're accessing one cell, you're perturbing some other cell also. This could manifest itself as charge reduction in some other cell. So these are the downsides that you get into. There are also lower level explanations that we may get into when we talk about RowHammer, for example, device level explanations. But that's the high level thinking. Your capacitor or your charge storage unit size reduces, and the charge storage unit size become closer to each other. And also the interconnects become closer to each other. For example, this bit line becomes closer to another bit line. This word line, which is not exactly shown here, the word line that's controlling this access transistor becomes closer to another word line. So there could be crosstalk across these interconnects, which also impact reliability of operation. So that's in general the downside of scaling technology to smaller dimensions. You run into these noise effects that are hard to control and sometimes hard to understand also. And we'll see a lot of that when we talk about memory robustness. Does that sound good? Okay. Feel free to ask questions. As I said, this is the goal of this course is to think deeply and critically. Okay, this I've shown you. This is the structure of DRAM actually. It kind of looks like a mesh. These are the cells. And this is a cross section on the side. This is another cross section. If you look at it, this is using a scanning electron microscope for a DDR5 cell. And these are the capacitors. You can see that capacitors are really close to each other, right, in the substrate. There are many other pictures you can find online, which is interesting. And this is the bit line. Yeah. Okay. So we've already discussed this also. Essentially, as you reduce the charge stored unit size and the size of all of the structures to sense, etc., data retention and reliable sensing becomes difficult. And I've given you some data from the field. This is our own data. In general, as I said, I trust my own data that I vet much more than I trust someone else's data that I didn't vet. So you'll see a lot of data from our work. That's really important. And it's really important that you can actually do that, right? The fact that we have a lot of data based on our own research is very special in my opinion. It's very easy to explain because I know that this data is real. Sometimes it's not true, right? It may not be real. If you read some paper, there's always a question, right? Is this real? Is this study done accurately? In the end, you put some trust, right? Here, you might put my trust in myself and in how critically I can analyze my own research and my own students' research. And I do try to be as critical as possible when we actually do this sort of research. That's really important to do justice. So you'll see a lot of data from our papers, but think of it as a good thing. This is not bias. This is, we do the science and we explain it to you. Teaching and education go hand in hand, right? So it's good to keep that in mind. It's better than me explaining some 1,000 random papers that I kind of have an idea of. Here, I have a really good idea of what is done in each paper. Okay? Of course, I also have 1,000 papers in my brain somewhere over here that I kind of have an idea of. And I'm going to give you some of those also, but that's, in my opinion, that's not the same thing, frankly. Okay? Okay, so I've already discussed this. This is a study that we did with Facebook where we showed that you can essentially, as if you there's a strong correlation between the density of the memory chip that's employed in a server and the failure rate that's observed for that server. And that's a very strong correlation. Clearly, we should all know that correlation doesn't mean causation, right? I think I saw a very good demonstration of this I saw recently was there was a roof and the roof was broken and a cat happened to sit on the roof on the broken part. And that's you can think there's a correlation clearly. Cat is sitting on a broken roof, right? Does this mean cat actually broke the roof? Probably not. So it's good to think about that. That's a very insightful example of correlation does not equal causation, right? So here, correlation again doesn't equal causation, but we actually look at this, and the cause of the errors, cause of the server failures are actually the memory errors that happen, and that cannot be corrected, or that can be corrected, but the correction also takes time. So a server fails for some time, and then it comes back again. That makes sense, hopefully. I should find that picture of the cat. Okay, so that's one paper that you may read as part of the homework. Okay, as I said, we're getting to where we were at the end of last lecture, essentially. We built a lot of infrastructure to also understand these issues at the lower level. Because if you do a study of a data center, this is actually a real data center running production code, lots of data centers across the world, lots of memory. You basically analyze how many memory errors you get across all of these devices. Think like 100,000 machines plus, more than that actually. And you try to understand what kind of errors you're getting. in the end, you cannot really isolate some things, right? You cannot know exactly why the errors are happening. For that, you need controlled experiments. So basically what you're doing is not a controlled experiment. You're really observing what's happening. And you're trying to, as much as possible, correlate things, but you cannot control. You cannot basically say, oh, I'm going to change the temperature, for example. Because you cannot control the temperature. That's controlled by some other mechanism in the data center, right? You cannot change it the way you like. You cannot set it to 80 degrees Celsius all the time. That's really controlled by the data center operator. So that's the sort of large-scale study that you can do. This gives you some insights, of course, but the insights you get into the exact error models are going to be limited. So what we normally do is to try to understand, try to build infrastructure where you can control things. And this is an example of an infrastructure, an FPGA-based testing infrastructure, where we can control things. We can design the memory controller ourselves. We can design the temperature controller ourselves. We can design the cooling system ourselves, like this fan, for example, over here. And then you can control, modulate different parameters. For example, in the memory controller, you can change the access patterns that you're accessing DRAM or memory with, reads, writes, etc. You can change the timing parameters that you're accessing DRAM with. You can change the temperature. And then you can say, okay, under these conditions, I observe these errors. So that's what we did for a long time. I'm going to talk about some of these, especially in the memory robustness lectures. This is the infrastructure that we had at Carnegie Mellon, where we did a lot of RowHammer studies. You're going to see that. And we open sourced this infrastructure. If you're interested in doing work in this infrastructure, there's a lot of opportunity. There's a newer version of it, DRAM Bender. And these are all used in academia and industry. You can see that there are different FPGA-based prototypes that we have for different types of memories. This is one of the examples where you can change the voltage with fine granularity, temperature with fine granularity. And this is our laboratory in the ETZ building where we actually have a lot of these, and we're expanding this. I'm going to give you a high-level overview of this. We're going to have actually lectures on robustness, especially, but I'll give you the high-level overview to begin with. One of the main reasons why we actually built this infrastructure was to see, as you reduce the size of this DRAM cell that I showed you, what happens to data retention capability? Does it become much worse? And how do we actually fix that? Right? So because the cell size reduces, right? As cell size reduces, the amount of charge you have in the cell also reduces. And in DRAM, it's dynamic memory. Over time, you lose charge. And you need to refresh memory, meaning you cannot retain data forever. You need to refresh DRAM cells. And as the charge storage unit size reduces, you need to refresh it more frequently, intuitively again. This is all intuition. You can model it in simulation also, in circuit level simulation. The question is this real? Like what are the measurements can we do on real DRAM chips to understand how bad is this problem? That's the reason why we built this infrastructure. You're going to see more of that later on. And one of the things we found using this infrastructure is not all cells are equal, meaning you don't need to, so the common practice in how you retain data in DRAM today is because DRAM leaks charge, you need to refresh cells periodically. Refresh meaning you basically inject charge back into the cells. We're going to see how exactly it's done. It's done using some commands from the memory controller. You inject charge back into the cells periodically. The question is, how often should you inject charge back into the cells periodically? That's a key question, basically. Because if that often is not often enough, you may lose the data inside the cell. If that often is too often, you're basically replenishing the charge too often, meaning you're doing this additional refresh operation a lot, which is wasting energy, which is wasting performance because you need to you cannot access the DRAM cell while you're actually replenishing the charge in it. So that's the fundamental problem. And how often at the time we were looking at this was 64 milliseconds. Basically, every 64 milliseconds, you refresh every single cell in DRAM. Imagine you have billions of cells. You're refreshing every single one every 64 milliseconds. That's a lot of energy, actually. In the data retention lecture, we're going to have you calculate how many megawatts, actually kilowatts, are spent of power is spent on this type of operation. It's kind of a waste. For example, in my pocket, the cell phone is refreshing its memory. While things are running over here, memory is being refreshed. Right. So the question we asked was, how often should we really refresh the charge? Should we really do it every 64 milliseconds? And if you actually really understand how good each cell can retain the charge, maybe you can do better. I'll show you this picture, basically. their data retention time profile of DRAM, all of the cells, billions of cells, look kind of like this. There's a small fraction of cells that are weak, meaning they can retain data. They need to be refreshed essentially every 64 milliseconds because this is their data retention range at some temperature. It's also very temperature dependent, as we will see, because as you increase the temperature, the charge leakage accelerates, and it actually accelerates exponentially, meaning at higher temperatures, you need to refresh DRAM cells much more often. So it's good to think about that. And if you have an infrastructure like what we have, you can test every single cell at some temperature level and figure out which cell can retain data for how long, right? And if you do that study, this is what you get. Sounds good, right? It's beautiful. Now I'm controlling the temperature. I'm controlling how long when I'm refreshing the cells, and I'm trying to figure out how long each cell can retain data. Now, the good news is most of the cells don't need to be refreshed at 64 milliseconds. You can get away with refreshing them every 256 milliseconds because most of them can retain data for at least 256 milliseconds. Now, if this is true, based on experimental analysis, now you can imagine, okay, there are many questions you can ask here, right? First of all, why do you have this picture? Right? Anybody who wants to venture? Why is there like this sort of heterogeneity in the data retention time of different cells? You have billions of cells. Some of them are very weak. Some of them are much stronger, at least 4x stronger. Let's say. Yes. Yeah. Constant, what's it? Okay, so let's take the first one, manufacturing errors, meaning heterogeneity in manufacturing. Some cells are small, some cells are large, because you cannot perfectly manufacture cells. Different cells have different amount of charge that they can keep. As a result, you need to refresh some frequently, refresh some others less frequently. That's correct, yes. The other one's also correct, like how often do you actually use access, but we control for that. We don't access them, essentially. So in this particular study, what we basically do is you put data into a cell, wait for n milliseconds, and see if you actually lost the data at the end of n milliseconds. Okay. So that way you can by testing for different n, you can figure out when the cell actually doesn't contain the data anymore. But if you're really accessing the cells, of course, when you access the cell, you're also replenishing the charge, which we will get to later on. But that's not in this equation. Yes. Mm-hmm. Yes, we're going to get to that. Yeah, yeah. This is just to give you an idea, but you're asking the right questions, basically. What are the other parameters that affect this, right? What is the data value, for example? Is it whether you store charge or not store charge inside a cell? Does it affect this? Whether you store charge or not store charge in surrounding cells, does it affect this? And it turns out that all of those answers are yes. So it's not a very simple equation like this. You need to do more testing, basically. Okay, but we're going to get to that in lecture 6 or 7. I don't know where yet. We're going to go into a little bit more depth. And these are really great questions because this sort of behavior exists in any type of memory, not just DRAM. It exists in flash, which we have a lot of studies on, but we're not going to focus a whole lot, at least initially. It exists in other memories like phase change memory, RRAM, in different ways. In that case, it's not charge, it's resistance levels. And those charge leaks, but resistance also drifts. Meaning you have a resistance level, but over time that resistance level changes, which is fascinating also. Okay. Any other questions over here? Of course, once you have this and you convince yourself, how can you take advantage of this becomes an also interesting question, right? Most of your cells are reasonably strong. In fact, at low temperatures, this picture becomes even more interesting. At low temperatures, many cells retain data for tens of seconds. Imagine I'm running at low temperature on my cell phone, maybe 40 degrees Celsius, maybe lower. And most of the cells, let's say 70% of the cells retain data for 10 seconds. But my cell phone is refreshing every single cell every 64 milliseconds. Imagine the waste, right? It's a huge waste, basically. You're wasting energy. And imagine this happening at the data center scale, right? These data centers, you're wasting a lot of energy in the end. So the scale of this problem is actually important. Okay, so basically this is the picture looks like this, no question about that. But there are a lot of issues to investigate over here. Clearly, the retention time of a cell is dependent on the location. It's dependent on the stored value pattern. It's dependent on temperature, which is not written over here, but it is true. It's also dependent on time, as we will see, meaning there's some randomness in the retention time, which makes things very hard. Just to give you an idea very quickly, these are, in my opinion, quantum-like effects that happen in hardware, especially scaled hardware to very small dimensions. When you test the retention time right now, the retention time may be 64 milliseconds, let's say. No, the retention time may be 10 seconds. So that's good. That's a good cell, right? You don't need to refresh it that much. But if you keep doing that, you may be doing the wrong thing, because this cell's retention time may be dependent on random factors that you don't fully understand, called variable retention time. And if you test the retention time 2 days later, it may go down to 64 milliseconds. So you probably would do the wrong thing and lose data if you actually change the refresh rate for that type of cell. So there are a lot of interesting issues over here, and some of which we're going to cover in a later lecture. But one of the major reasons why we actually wanted to build this infrastructure was to test a lot of these hypotheses. So in this work, which is actually one of the early works on memory scaling, at least in the recent years, we basically said that there is this heterogeneity in DRAM, and we can actually exploit it relatively simply. And then we wanted to really test whether we were right. So it's good to have this hypothesis and actually write a paper that says, if this is true, this is the benefit you would get. And in this paper, which we're going to see later, you can actually get a lot of benefits by adapting the refresh rate to the cell. So if you actually don't refresh all cells equally, refresh the cells at the rate that they need to be refreshed. And then we basically said, can we actually make this happen in real? That's why we built this infrastructure. That's one of the major reasons. And we're going to see a lot of these works. This actually enabled a lot of works by us and others. I'm going to flash through this because we don't have time. But it turns out it's not easy to do this. There are things that you need to do. This paper, by the way, received the Test of Time Award at DSN because it's a very good solution to this problem. In my opinion, it's not the perfect solution, but it's a very good solution. And then there's more to do. I'm going to skip these because we will have another lecture on this topic. And this is, if you're not patient enough, this is the lecture from 2020 in the same course. Okay, but hopefully this gives you some idea of what we're going to examine in terms of scaling issues, especially robustness issues. Any questions? Thoughts? Any solutions to this problem? Okay, you'll see more solutions when we get to the details. But let me talk about some other scaling issues, which we're also going to cover in more detail later on. So with the infrastructure, with the type of infrastructure, FPGA-based testing infrastructure, you can do a lot of studies actually. In the end, your creativity and also the capability of the infrastructure is limited. So having this sort of infrastructure is special, and I believe it's a one of a kind infrastructure that we have here. So if you have some creative ideas, we can test if the infrastructure is capable of testing those creativity of the ideas, and you may discover something that's very interesting and important. And one of the things that we discovered with this infrastructure was the RowHammer phenomenon. How many people know about RowHammer here? Okay, that's good. Where did you hear about RowHammer? Oh, seminar. Okay, you attended the seminar. You also attended the seminar? Oh, okay, hardware security. Okay, yeah. Great. Yeah, this is a hardware security problem. That it became a hardware security problem. But I'm going to give you the high-level overview today, but we're going to go into a lot more detail. It may be useful in your hardware security course, for example. How many other people are taking hardware security at the same time? Okay, great, yeah. Yeah, there's certainly a good synergy between this course and hardware security. Clearly, this course doesn't only talk about hardware security, but hardware security is a really important aspect of computer architecture today, especially. Okay, so basically, RowHammer is a phenomenon. Again, it's a technology scaling phenomenon, and it's the fact that you can predictably induce bit flips in DRAM memory chips. It was documented in this paper that we wrote in 2014. Essentially, this is commodity DRAM chips, real DRAM chips. And all recent DRAM chips are fundamentally vulnerable. Originally, when we studied this problem, we saw that more than 80% was vulnerable. Today, actually, everything is vulnerable because of technology scaling, as we will see. And it's really a data corruption problem. Essentially, you corrupt data by accessing some other data. That's the very brief explanation of it. The mechanism we will discuss in a little bit. And it's also the reason you're studying this in hardware security is it's a hardware failure mechanism that actually creates a widespread security vulnerability because you corrupt some data and that data corruption is exploitable using essentially by hackers, let's say, using some smart attacks. And we'll see some of them, but if you really want to know more of them, you're going to read some papers, but also if you want to implement some of them, you can take the hardware security class. And it's fascinating because people write articles that look like this. Forget software, hackers are exploiting physics. That's true, I like that actually. Okay, this is the first paper that documented it. Let me give you the high level idea. So essentially, this is a two-dimensional array of memory cells, DRAM cells. All memory looks like this actually at some level. In this case, you have some number of rows and on the you have some number of columns. Each row may be 4 kilobytes, 8 kilobytes, doesn't matter. We're going to see more of that later tomorrow. Later today or tomorrow. But two-dimensional array of cells. And this is the word line that you kind of saw when we looked at the access transistor. It controls the access transistor. Anyway, it doesn't matter. If you want to access one cell in a row in DRAM, or in many memories actually, you basically need to activate that row. Apply high voltage to this word line. In DRAM, what happens is you apply high voltage to this word line, it connects the capacitor to the bit line, if you remember that capacitor picture. The capacitor gets connected to the bit line so that you can sense what's the charge in the capacitor. You do it concurrently on many cells. That's why it's a row. And the reason we have the structure is we need to have high density. We don't want to control a single cell when we access something. We want to control many cells so that we can actually amortize the cost of accessing cells, because we want to improve the density. If you access only one cell, if you are addressing only one cell internally, the peripheral logic to access that cell dominates the cost. If you actually aggregate such that you can do an access in the two-dimensional array, you can actually reduce the cost of the peripheral logic, like the row decoder, column decoder, etc. Okay, so you access DRAM, you apply high voltage to that word line. So you get one bit, you sense one of the bits. That's good, all good. This is an access, basically, activate. Now, if you want to access some other row, you need to undo what you've done. And you basically close this row that was open, apply high voltage to that word line, low voltage to that word line. This is called a pre-charge in DRAM. It has a special meaning. You'll understand what a pre-charge is later on, again, when we talk more about DRAM. Make sense? Now, this is all legal operations. Now, it turns out if you keep doing this repeatedly, activate pre-charge, activate pre-charge, activate pre-charge, completely legally. We're not violating anything in DRAM. Completely legally, enough times before the cell gets refreshed, it turns out some vulnerable cells in physically adjacent rows lose their data and they get corrupt. So if they were storing one, for example, every time you do this activate pre-charge, activate pre-charge, activate pre-charge, these adjacent cells, physically adjacent cells that are not in the same row that you're modulating, lose their charge little by little with every activation. And if they're vulnerable enough, they lose their charge if they don't get refreshed. They may lose their charge beyond the point of recovery, meaning you cannot basically their charge gets depleted. That's the idea. And this is the RowHammer phenomenon. These X's are corrupted cells. And when we actually clear, this should not be happening, right? Because we're accessing memory. We're just trying to activate a row and then close it. We're not even reading from memory actually, but activation is it enables reading. You sense the database. Nothing should be changing in memory, right? Because we're not writing to memory for sure. But it turns out you're actually changing the data in adjacent cells. So we call these the victim rows, basically. And the reason this is happening is cells are essentially too small and too close to each other. That's basically the essential reason. There are many device level reasons that we'll not get into. Crosstalk, for example, electromigration. These are the two major reasons. And these keep changing also as technology evolves. changing, meaning there are other reasons as well, and also some of them become less dominant, more dominant at the low level. Then if we have a RowHammer lecture, maybe we'll go into that. But basically, cells are too small and cells are too close to each other. The fact that you're accessing one cell is affecting the other cells because they're too close to each other and there's noise that's happening. Okay. So this is our data from our original paper. Essentially, we tested 129 modules at the time. These are DRAM modules using our infrastructure. And we found out that newer modules at the time were all vulnerable. And older modules were not vulnerable. So basically, at some point, this problem became too bad that you would be able to induce enough activations before the cells get refreshed. Meaning, within a 64 millisecond refresh interval, you would be able to do enough activations to corrupt the adjacent cells. Yes. Uh-huh. I see. From an attacker perspective, yeah. I'm going to give you some examples. Yes. So, if, for example, you can corrupt memory, someone else's memory, not your memory, right? Because you may be actually located with someone else in a data center, and you may want to corrupt someone just for fun. But you can also hackers are quite intelligent. You can also, for example, figure out how to do this attack such that you induce these bit flips in the right place in the operating system structures, such that you gain root access to the machine. For example, what I showed over here, the victim rows may belong to system level page tables. We'll talk about virtual memory. Do you know about virtual memory? Okay, if you know about virtual memory, that's good. If you don't, we may actually cover it. But this is in DDCA, Digital Design and Computer Architecture. You can take a look at it. Basically, they could be including page table bits that enable write access to your kernel pages, for example. And if you actually flip those bits, now you actually have a pathway to write to your own page table. Actually, it could be a page table entry pointing to your own page table. This is how actually original folks from Google enabled an attack. So that's one example. And there are many other. If you flip a bit, this is actually a fascinating phenomenon. You have a very good question. If you flip a bit, what can you do? That's what you're getting at. If you can, in fact, I would actually make it stronger. If you can predictably flip a bit, if you know which bit you're flipping, what can you do? You can also do more statistical attacks where you can recover cryptographic keys that you don't have access to. And there are actually a lot of security works on that topic. You can induce these bit flips in, let's say, an ML inference program, and you can reduce the accuracy of that significantly. There also works on that topic. So I'll give you an overview of that later on, not today, but that's a very good question. And probably you cover some more of these in the hardware security class. Yes. Yeah. There are many works. Now we're having a RowHammer lecture. These are very good questions, basically. But basically, what happens is charge leaks from the capacitor of the adjacent cells because of electromigration. Electromigration is a big effect, essentially, because you're doing some. These two rows share a substrate in the underlying hardware, same semiconductor substrate, and the fact that you're actually inducing some voltage change in one row is causing migration of electrons from a cell in the same substrate. So that's one reason. And there are actually device-level papers that try to model it. So there's actually a lot of device-level works that model this phenomenon and tries to explain it. When we get to the RowHammer lectures, I'm going to show you some examples of how these electrons exactly escape, hopefully. So that's a great question also, basically. Is it possible to change from 1 to 0, 0 to 1? It actually happens both ways, but yeah, let's get to that later. Yes. It's also a very good question, basically. As cells age, does this become easier to induce? There's some evidence from our papers that it is it becomes worse, but there needs to be more studies in that direction. That's actually a really great area to investigate because aging is a very dangerous topic, in my opinion, that not many people think about. So from a limited experimental evidence, yes, but there needs to be a lot more experiments to be done. Because aging is also a difficult thing to study. Like, how do you age? Right? What are the mechanisms for aging? Good questions. Okay. All right, we'll have a lot more in the RowHammer lecture. Okay, but basically, older chips were not as vulnerable to this. And part of the reason is maybe we did not know exactly how to make this work. Today, with today's knowledge, actually, we know a lot more about how to induce these bit flips. But we're going to get to that also. Okay, the interesting thing is, okay, this was our FPGA infrastructure. This testing is with our FPGA infrastructure, and our paper has a lot of results from FPGA. But we also asked the question, can you actually induce these bit flips through a real program, meaning a user-level program that's executing on a CPU, not an FPGA? So this is a real CPU, a real memory module. And this is the program that we wrote and open sourced. And what this program does is it selects addresses X and Y such that they go to the same subarray. And it basically tries to avoid cache hits in the CPU by flushing X, and it avoids row hits in the memory controller in the DRAM, because there's a row buffer in DRAM over here that are the sense amplifiers that are not shown. But if you want to access some other, let's say, location in row X, you want to close the row buffer, avoid the row hits that happen in the row buffer over here. That's why you need to do this ping-ponging. Basically, you keep reading X and Y, activating X and Y, and pre-charging each of them, activate pre-charge to each of them. And if the chip is vulnerable, you'll get bit flips. So that's the idea, basically. And this is a real program. You can also download and execute it. It's a bit old right now because it's from 2013 or so. The better version of this program was developed by Google, that built on this program that made it better. But there are much better versions of this program right now that you may be studying in hardware security, for example. Yes. Okay. It's sold by this slide. Okay. Yeah. This is the example is basically you flush the cache blocks from the cache using some instructions. If these instructions are not available in your instructions architecture for some reason, security researchers have developed many ways of getting rid of things from your cache, because you basically can evict the cache blocks that you don't want from your cache by doing a lot of other accesses. Okay, I'll not get into that again, but there's a lot of security literature to kick stuff out of your cache that you don't want for many reasons. Okay, so this is also interesting. Again, in RowHammer lecture, we'll go into more depth, but it turns out there's something called double-sided RowHammer, which we analyzed in our original paper. If you sandwich one row between X and Y, essentially there's only one row between X and Y, you induce many more bit flips, and you induce the bit flips earlier. The reason is you're causing a lot more disturbance by doing this hammering on both sides of a single row. This is called double-sided RowHammer. It's going to be more and more important in the future. Okay, so basically in our original paper, we reported a lot of errors in real systems using this program. You can see the errors. Again, it's not important. The number is not important. The fact that you can induce the errors is the most important part. But in some cases, the errors are huge also, which is also interesting, right? That means it's a big problem. And we argued that that's really a big robustness issue, not just a reliability issue, but also a safety issue. No one should be able to induce these errors. But your own program should not be able to induce these errors also. It's a security issue. We basically argue that if someone is able to design a program that takes advantage of these bit flips, they can hijack your computer. That's exactly what we said in the paper. And later, folks actually showed that, which is good. So this was our paper. We're going to see more of this later on. Maybe I'll read the first sentence. Memory isolation is a key property of a reliable and secure computing system. And access to one memory address should not have unintended side effects on data stored in other addresses. And this is very real, in my opinion. That's the isolation, basically, between different addresses. And we said, again, someone can hijack your computer. We said someone can crash your computer. This was discussed earlier. That's benign. Well, I wouldn't call it benign necessarily. That's a benign security attack, crashing your computer. But actually, this is also a bad denial of service kind of attack, right? Actually, real cloud providers, for example, who take programs from many different places, are very worried about that. What if actually someone calls a denial of service by crashing a lot of servers? They may get caught, but they could be actually doing this repeatedly, right? Maybe you cannot catch them all the time easily. Okay, it's good to think about crashes as a security problem too. They're definitely an availability problem, but they're also a security problem because they could be denying service. Okay, these folks from Google Project Zero basically took our program and also findings in our paper, and they showed that you can actually induce these bit flips in real laptops, and you could, using a user level program, and it can become root on that laptop. You can basically gain kernel privileges. And that's the security attack. And that has started a large investigation into security exploits of RowHammer. I think we kind of discussed this based on your question earlier, but you can exploit RowHammer to take over a system completely, get all kinds of privilege you want. This is something we didn't discuss. You can actually exploit some data dependence properties of RowHammer to read data that you do not have access to. We're going to see that hopefully in the detailed RowHammer lecture. Essentially, you can break some privacy or confidentiality. You can break out of virtual machine sandboxes. We're going to see that a little bit. You can corrupt important data, meaning render ML inference useless. In fact, there's a paper at Unic Security this year. Unic Security is a top security conference this year in August, a couple of months ago, which showed that on GPU memory, you can induce these RowHammer bit flips. That's the first paper that shows after 12 years, as you can see, on GPU memory, existing GPU memory, you can use bit flips, and you can essentially render ML inference useless. That's what they were showing, basically. Other people have shown this in CPUs, etc., but GPUs also special today. And also, you can steal secret data like cryptographic keys or ML model parameters, and there are a lot of works that show this. Okay, so we're going to cover this more. We have a lot of papers. Some of these will be suggested. So we wrote this retrospective in 2019, saying that there will be worse things to happen. And worse things actually have happened since then. But this is still a very good overview, in my opinion. Even though it's from 2019, it covers a lot of the research and the perspective of what has happened to RowHammer until then, and kind of our predictions of what will happen. And I think what has happened is really interesting, but we'll see that later on. So we updated this more recently. And this is Giray's thesis. Giray is one of my recent students who has graduated, and he actually developed a lot of, using our infrastructure that I showed you, he developed a lot of insights into the behavior of RowHammer. For example, how does RowHammer bit flips change with voltage, which was not investigated at all before. And he basically showed using real system infrastructure that by changing the voltage, you actually have different vulnerability to RowHammer. That's one example. There are many, many other examples that they have found. He looked at the spatial variation of like which cells are more vulnerable, which cells are less vulnerable. Let me give you the basic insight that he found. Essentially, there are some cells that are extremely vulnerable to RowHammer, but most cells are not that vulnerable. So if you can somehow figure out this distribution, you can design a much better solution, much more efficient solution. We didn't talk about how to solve this problem yet. We're going to talk about that. But you can design a much more efficient solution. That's why understanding what's going on in real chips actually enables you to develop much better solutions also, in addition to some fundamental understanding of a fundamental problem. So these are actually all discoveries in the field. We'll talk more about that. So Giray is now a faculty member. He just started at the CISPA Helmholtz Information Security. But his dissertation actually won 3 major dissertation awards, and it was a finalist for others, 2 others, which is actually a very good thing. I'm proud of him. Yeah, it's hard to win even a single award as a dissertation. 3 + 2 is actually kind of fascinating. Okay, so this happens in essentially all types of DRAM, HBM also. We're going to talk about high bandwidth memory, 3D stacked memory. This is used heavily in GPUs today because they enable high bandwidth data supply to a machine that needs high bandwidth data because it's executing these highly parallel operations in machine learning and other workloads. So essentially, GPUs are also vulnerable, and we do a lot of studies on that. Okay, so we're talking about scaling. I'm going to also essentially these scaling problems will happen more and more. This is a recent discovery, again, from my group on using our infrastructure a couple of years ago at ISCA. It turns out this is a different disturbance mechanism. We're going to study this even more in the robustness lecture. But in RowHammer, the idea is you activate a row as frequently as possible, right? As allowed by the standard, legally. You don't basically violate anything in terms of the DRAM chip standard, etc. And that induces, you need some number of activations to induce bit flips. In row press, you activate the row and keep it open for some time. You don't send the pre-charge command, basically low voltage command, if you think about it. Quickly, you keep it open. Let's say you keep it open by some amount allowed by the standard, in this case, microsecond, you can see, which is possible to do, especially if you have an FPGA-based memory controller, because we can control everything, as you know. Now, if you do that, it turns out you cause more disturbance in adjacent cells that is fundamentally different in nature compared to RowHammer. Again, this goes to device level, but I'm not going to describe it right now. But it enables you to induce bit flips with much fewer activations. In this example, 47K becomes 5K, for example. So it can basically induce bit flips with much smaller number of activations. So there are two issues over here. One is this is a different device level mechanism. And when we actually wrote the paper, there was no low level understanding of it. There is no device level paper that describes row press, sorry. That's not exactly true with RowHammer, but that's a story for a different time. Later, people who were interested in device level investigation read our paper, and they basically said, okay, let's model this at the electron level, what's happening. And they actually figured out how this works at the low level. This is actually very interesting because normally what happens in technology development is you develop a new material, for example, right? And that new material, you understand the characteristics, and then you investigate, you build a device on top of it, you understand the characteristics, and then you build a system on top of it. That's very bottom up. Normally, you understand a lot of characteristics at the low level. The discoveries at the high level are relatively limited. This is why also some people think the high level is not so fundamental, right? That's not true exactly, of course. We know that because you can invent algorithms, etc. But basically, here we have a lab where you can actually discover a new phenomenon that no one has documented. That's fascinating to me, right? Because this technology, it's not a new technology. It's been around for 60 plus years, right? And we're still discovering new things about it. And the reason we're discovering new things about it is because it's scaled to a level that is very small. And understanding the effects at this level is very useful, in my opinion, not just for this technology, but for other future technologies that we may actually build that will scale to maybe even smaller levels. So it's good to think about it that way also. Okay, anyway, that's kind of another story. But that's one interesting thing about this. The other interesting thing about it is, let's assume that you designed a solution to RowHammer. Let's say one solution is after 40,000 activations, you refresh the DRAM, refresh that bank. You refresh adjacent rows. These are some solutions that we have proposed in our research. That's all actually implemented in real chips. And you set your threshold to, I don't know, let's be a little bit aggressive, 10,000. Because you know that 47,000 is the point where you will get bit flips. Now there's another mechanism that someone can use that bypasses your solution, right? Because your threshold was not low enough. So it's good to think about that. Okay, so these are real chip results that show row press. When we talk about robustness, we'll see more of that. And you can see that, again, these are three major manufacturers, Samsung, Hynix, and Micron. And you can see that the number of activations to induce a bit flip, AC min, reduces by 1 to 2 orders of magnitude in legal, actually, in times that are allowed by the standard. Fundamentally, it reduces to 1, actually, if you can keep the row open long enough. Okay, so this is just a summary slide of the scaling issue. So this is what, I think this is a very good depiction of scaling. Non-scale technology, cells are large and far away from each other. As technology scaling happens, cells become closer to each other and smaller. And as a result, cells become less robust. And this is data from our work over the course of, let's say, 10 years. You get 100x reduction in robustness for some robustness metrics. In this case, how many activations do you need to induce a bit flip? So how do you solve this problem? I'm not going to go through all of the solutions, but one of the solution directions is actually designing intelligent controllers to fix this problem. Right? And when we talk about robustness lecture, we're going to look at much more solutions. But I think this is a very good solution direction because this is a very principled solution that doesn't require a lot of change to a lot of cost or change to the device, etc. I'm going to give you what that intelligent controller is. Basically, a controller that understands what's happening to the memory, and also that understands what are the characteristics of memory, under which conditions the memory will fail, and it tries to prevent those conditions. That's the idea. Basically, a memory controller protecting memory, doing what it's supposed to be doing, if you think about it. If you ask the 10-year-old, maybe, what should the memory controller be doing? Protecting memory, right? They would say, especially with a 10-year-old mindset, yeah, you need to be protecting the memory. But yeah, that's the idea. Okay, so we've argued for this in many papers, some of which you're going to read. This is some more recent work that we've described. And the good news is, like we've been doing the research in this area for 15 plus years. And the good news is industry, even though they were a bit slow to begin with, they now recognize the problem much better, especially after 2020. They put a lot more effort into doing the right thing. I'm not sure if they're still doing the right thing, but they're doing something better this time. This is a paper from SK Hynix, which is one of the major manufacturers in a major conference, solid state circuits conference. And they basically describe their solution to RowHammer solutions. There are multiple solutions. And this is also the first paper from a major manufacturer that acknowledges the problem. And you can read it if you're interested. And the idea of a solution is actually something that, in my opinion, is in the right direction. Basically, you have an intelligent controller or slightly intelligent controller. I'll give you the basic idea. You can think about whether or not it's a good idea later on, especially when we talk about robustness. The idea is inside the DRAM chip, you have a controller. So what does this controller monitor? You add some additional cells next to each row in DRAM that count how many activations happen to that row. Activation counter. Per row hammer tracking, that's what they call. Per row activation counters, that's the standard calls. Essentially, for every row, you have an activation counter. These activation counters internally get incremented with every activation, and maybe other things. You need to take into account row press. You got to be careful over there. And if that activation count becomes greater than some threshold internally, so there needs to be some computation logic to figure that out, of course, then the chip internally, the intelligent controller inside the chip takes an action. Right? They don't describe exactly what that action is, but it's probably refreshing some adjacent rows by some amount. How many rows to refresh? When to do this? They're all very good questions. Yes? Yeah. So we're going to cover a lot more of that in the robustness lecture. But the question is, yeah, where do you put this intelligence? Do you put it inside the DRAM chip, or do you put it in the memory controller on the memory side? That's a very good question. Maybe we can have that discussion later on. Initially, actually, people put it inside the memory controller on the processor chip. Right? Intel, for example, had PTRR mechanism, terrible naming, probabilistic target row refresh. Essentially, it's very similar to what we had proposed in our original paper, probabilistically refresh adjacent rows. Now, the difficulty on the host side is you don't have perfect visibility inside the memory chip, right? You don't know exactly which rows are adjacent because internally there's some remapping of the addresses that happen. So I think the solution is actually more robust compared to preventing it, at least in that way, from the memory controller on the processor chip. But there are also downsides to the solution because the DRAM chip doesn't have enough freedom to actually take some of these actions. We're going to cover this more. But that's a very good question. Where do you put the solution? Another question. Yeah, go ahead. Mm-hmm. Mm-hmm. Yeah, yeah. Mm-hmm. Yeah, yeah. Mm-hmm. Exactly. Mm-hmm. Mm-hmm. Yeah. basically somehow at the software level detect that a program is trying to do RowHammer, right? Trying to activate a row many times. That's what you're suggesting, right? Yeah. I see. Yeah. I mean, it's very difficult to do things at the software level because a program. First of all, you need to understand what the program is doing. That may be difficult, but people have proposed solutions that try to track performance counters, for example. How often a program is trying to activate a row. If you can somehow guess that quickly enough before the program actually activates that many those rows, you may be able to do some things like to fix it. But as you said, it's not very efficient in the end, especially at the thresholds that we're at today. The number of activations to induce a bit flip is on the order of today 1,000, let's say. It's very difficult to detect that number at the high level, at the software level. There's not enough communication from the hardware to the software. But it's good to think about these ideas. I like the thinking. And there are actually a lot of innovation on the software side in different ways. Even there were RowHammer papers at the SOSP, like Symposium on Operating System Principles, which is fascinating to me that they also have RowHammer papers, but they have a different solution. We may talk about that. Cool. Okay, great. Okay, but this is the gist of the solution developed by a major manufacturer, and they actually manufactured their real chips, prototype chips, to look at that. There are, of course, potential issues over here, which we will discuss again in the RowHammer lecture, but this sort of solution was recently standardized in DRAM standards. JEDEC is the industry standardization body that standardized a lot of things in DRAM, memory, storage, etc. And it's called per row activation counters right now. It's good to think about it. This is actually very fascinating because it's very difficult to change DRAM chips. It's very difficult to do anything in DRAM. But the fact that we were able to induce this sort of big change is a positive sign. So the question is, of course, are solutions good? Right? This is one solution to a problem. You can guess what the problem is. You can also guess whether the solution is good. You don't need to be a 10-year-old to say this is a terrible solution. I think hopefully even 90-year-olds would agree. Yeah, basically it's not a good solution, right? Basically, under what conditions is a solution good solution? Under what conditions is a bad solution? And again, in the RowHammer lecture, we will study some of these. So we actually evaluate these industry solutions. This is one of our recent papers that shows that maybe the solutions are not as good as they should be. And again, I'm going to leave this for the robustness lecture. So it's good to always question things. That's my point. And we propose better solutions than what is proposed. Because one of the reasons the industry solutions is not that good is it's to solve RowHammer, to activate. So internally, the DRAM chip needs to maintain activation counters. And to increment the activation counters, you need some time, especially if you cannot do it in parallel with something else. And to get that time, this per row activation counter solution increases some of the timing parameters in DRAM, which really affects performance, essentially. And we argue that this is not a good solution in terms of performance because you increase the timing parameters. Here's a solution where you update the counters in parallel with the activation so that you actually don't increase the timing parameters. Right? So basically, that's one of the ideas in this paper. Let me give you, yes. Mm-hmm. Mm-hmm. What do you mean refresh the cache? Like which cache?
So basically, let's say I access one cell.
Mm-hmm.
If I were to access a cell which is adjacent to it, the next access will happen from cache, and there is no possibility of RowHammer.
Mm-hmm.
But if I were to access something which is not in the cache, then there exists a possibility of RowHammer. So what I'm suggesting is instead of modeling things for access in the loop, what if we model it on the basis of reusability in the cache?
Okay. Yeah, so these solutions don't care about the cache, right? This is happening in the memory controller, meaning the activations are coming from the cache. The reuse already happens in the cache. So if nothing is coming to the memory controller, these solutions don't increase the activation count. So I think these solutions are already doing that. Make sense? Yeah. Okay, let me give you another idea. So one of the issues with having a memory controller that actually dominates DRAM is DRAM doesn't have time to do things. And actually, that is true in this solution that industry proposed. There's not enough time for DRAM to do things, meaning sometimes the DRAM is not able to solve the problem very well. So in this work, we propose a much better solution in our opinion. We're going to discuss that later on again. But just to give you an idea, a high-level idea of the solution. So you have a memory controller today, which is on the processor side, and you have a DRAM chip, which is on clearly the memory side. And normally what happens is this memory controller dictates everything this DRAM chip does. DRAM chip doesn't have enough time to actually optimize itself. So our idea in this work is to enable the DRAM chip to have some breathing room so that you can actually do things internally, autonomously, without the memory controller initiating things. So this refresh is an example of this also. So what we do is we basically give that freedom to the DRAM chip by changing the interface just a little bit. We enable the DRAM chip to say no to the memory controller. So the idea is if the memory controller wants to activate a row, the DRAM chip can say, no, I'm busy at this place. Meaning the row you're accessing, that area, I'm doing something to it. Maybe I'm doing RowHammer protection. Maybe I'm doing refresh. Maybe I'm doing some kind of other security maintenance, right? I don't want no one to know. Basically, that's the idea. So it's fascinating that this sort of thing doesn't exist in today's systems. Even though memory is so important, memory has no capability to do things by itself. Right? We're very processor-centric in our thinking. So that's the idea. This way, we believe you can partition the work much more nicely between the memory controller and the DRAM chip. Memory controller can do, for example, scheduling of operations that are coming from the processors or the accelerators. But the DRAM chip can do what it's really good at, meaning optimizing refresh, for example. It can figure out what parts of it to refresh frequently or not so frequently. Today, the way refresh is done is memory controller says refresh, refresh, refresh. Every n microseconds, the memory controller sends a refresh command to DRAM, and the DRAM chip refreshes internally. Without that refresh command, DRAM chip cannot do anything. It's kind of dumb, right? So the idea here is very intuitive. The DRAM chip is internally doing its refresh operations, scheduling them, deciding how often to refresh, what to refresh, when to refresh. All of those are given to the DRAM chip, which the manufacturer knows much better than the memory controller designer in general. And when the DRAM chip happens to be refreshing a particular part, it just says no to the memory controller. Memory controller, I'm not going to obey your request this time. Try it again. So that's the idea. So with this, you can actually optimize a lot of these mechanisms nicely, which I'm not going to go through again, but you can read the paper, or again, in the robustness lecture, we're going to go into more. But the idea is, again, this came out of a questioning, right? Is this the right interface between the memory controller and the DRAM chip? Should memory controller dictate everything that the DRAM chip does? What is a better solution to all of these problems that we have in scaling? And once you critically question this, you realize relatively quickly that this is not the right, the previous interface is not the right interface. If you give some freedom to the DRAM chip, you can actually do a whole lot better. The question is, what level of freedom do you give, right? Does this interface, so this is a very simple change, very little change to the chip and the interface. You could also change the interface completely, meaning memory controller, for example, sends a request to the DRAM chip, and DRAM chip decides how to schedule everything, right, internally. That's another way of changing the interface. There could be packets communicated between memory controller, the DRAM chip, and the DRAM chip accumulates those packets and decides when to respond. It can respond out of order, etc. It could do many things. So this change is much simpler than that sort of heavy change. Okay, again, I'll go through this relatively quickly, but that's the idea of self-managing DRAM. It's good to think about this in when you go through, let's say, the later lectures. Can we actually have a better interface between the memory and the memory controller? Okay. I'm going to take a break after I finish this scaling part. But there's more to come in scaling. So you mentioned aging, for example. It turns out RowHammer becomes worse with aging. Meaning if you don't have a good enough memory controller, if you decided your thresholds, assuming there's no aging, maybe you'll get bit flips in the field, right? So that's not good. But this is an area that needs to be studied a lot more, in my opinion. This is the paper from Girai that studies it in some detail. More recently, we also discovered something, again, that was not documented by anyone so far. They're called variable read disturbance. The idea is, again, this is more like a quantum-like effect. The read disturbance threshold, the number of activations to induce a bit flip in a row, it turns out changes randomly, unpredictably over time. There's no way we can model it using a predictable model. It's random. And that's why I call it a quantum-like effect. We don't know the exact reasons for it. We have some hypotheses, and there's no device that will work. But essentially, this says that if you configure your, let's say, defense, assuming that one of the rows is vulnerable for some activation count, that activation count may reduce significantly 2 days later. So there's a danger over here. So this actually requires an even more intelligent controller that really understands what happens in the DRAM. And I believe this is going to get worse. So there's more data that we're collecting. Yes. Yeah, that's a very good question. Basically, there is certainly a RowHammer type of thing in NAND flash. It's not called RowHammer. We actually studied it earlier than RowHammer, and that's one of the reasons why we actually started looking at RowHammer. There's read disturbance mechanisms in NAND flash. Yes. In fact, whenever you read a row in NAND flash memory, it turns out you apply some reference voltage to that row. But for all of the other rows that are in the same, I'll call it a subarray for now, in the subarray, you apply much higher voltage to inhibit them from actually communicating their data to the bit line. And actually, you cause a lot of disturbance because of that. So there is a very similar mechanism. The good news in NAND flash is there's a flash memory controller that takes that into account. And that's the thinking or the mindset in NAND flash is that controller needs to be very careful. It needs to be very intelligent, and it should prevent these issues. But when we cover SSDs and NAND flash, you'll see that there's an equivalent of RowHammer. Very good. Okay. And I believe there are equivalent mechanisms like this also in different memories, but we were just discovering them. Okay, the question is, if you actually keep discovering this sort of things, how do you actually build a system that's safe, secure, robust, right? If you're interested, there's more discoveries to be done. Okay, so you mentioned NAND flash. I'll mention phase change memory, for example. What about emerging memory technologies? We have a lecture on emerging memory technologies, but just to foreshadow it, you may think of, there are many memory technologies that people have developed over many years. There's NAND flash, clearly. This is very popular for good reason, as we will see in the NAND flash lectures. There's SRAM, but there are also some other technologies that are not as, let's say, prevalent or popular because we don't know how to fabricate them at low cost and reliably yet, but it's good to investigate those areas also. This is an area that we had done a lot of work on, for example, phase change memory. This is a paper from 2009, as you can see. And you may say, for example, how does this sort of scaling issues affect other memories? I'm giving you the NAND flash answer for RowHammer. There are also other scaling issues in NAND flash, but some of these other memories actually have other problems, like endurance problems. NAND flash also has this problem. Endurance problem means that whenever you write to a cell, you weaken the cell in some way using some mechanism that depends on the memory. And every write to a cell weakens the cell. So at some point, you cannot do another write to the cell because the cell is dead. Dead is the definition of dead is you cannot read the data reliably from that cell anymore because you wore out the cell. This is also called a wear out problem. It's the endurance wear out, if you hear that. That happens in some memories. DRAM, as far as we know, doesn't have this wear out problem as bad. At least no one has demonstrated that you can wear out a DRAM cell. That's a good challenge for people. If you can demonstrate that, that's actually a very big discovery, in my opinion. But I haven't seen anyone demonstrate that yet. But some other memories are very well known, like flash memory. You do, depending on the technology, depending on how much data you pack, you do 1,000 writes to a cell, and after that, you should not do more writes. Phase change memory is another example. This means that fundamentally, you do need an intelligent controller to manage this memory, right? Because how do you ensure that you don't do more than n writes to a particular location? You need to design a memory controller that understands how many writes you do, and at least tries to avoid doing more than n number of writes to a location. So that's why that's one of the reasons why these technologies actually require intelligent memory controllers from the get-go. And flash memory actually has always needed an intelligent memory controller for this reason, right? For other reasons also. So it's good to think about different memory technologies, and we're going to look at those also. But don't think that they don't require, let's say, they don't run into scaling issues. All memory technologies run into scaling issues at some point. And some of these technologies have not been examined as much, have not been pushed to the limits as much. We have kind of pushed DRAM and flash memory to the limits. We still keep pushing them to the limit by reducing the cell size. But some of these memory technologies that are investigated, both in industry and academia, they start with large cell sizes. As a result, people may not see those vulnerabilities early on. The question is, what happens if you actually scale to very small cell sizes that actually enable the capacities that we have today? Okay, so we're going to have fun with the emerging memory technologies lectures, I think. So, but regardless, I think building a laboratory to understand and discover things in memory is really important, because that really pushes the boundaries, and it's very invaluable in my opinion. You may do a lot of simulation, etc., to really understand device. That's also very valuable in a very different way. But having some grounding on using real devices, and also trying to figure out what are the challenges real devices face under different conditions is really important. That's why we keep expanding it. And people who are interested in this, we're happy to get help from you. Okay, I'm going to take a break after I show you a couple more slides. The good news is, so actually, maybe in the RowHammer lecture, I give you some other stories. But when we first wrote our RowHammer paper, it was rejected from a top conference, Micro. They basically said, this is not an important problem. Or some other folks said, go and publish somewhere else. Because this is not for us computer architects, which are the rulers of the world, right? Don't bother us with this RowHammer thing. Let the DRAM manufacturers solve this problem. Now, the good news is, I think, but clear, this is real data, right? It's very, very hard to say these things if this is really happening in a real device and real phenomenon, and we believed in that. And then we actually published it at ISCA, so we resubmitted it. And after we resubmitted, actually, there were 6 reviewers. 2 of them still rejected the paper. And one of the rejection reasons was very interesting. We were talking about 2013. The reason was industry has already solved this problem. Which is very interesting, as you can see, right? This is 2013, where in 2025, industry still hasn't solved this problem in a good way, but they're trying, of course. But yeah, so it's good to think about a global perspective also, right? You do the right thing, you do all of these studies, build the infrastructure, you may still not get accepted, basically. Then how do you deal with it is a good question. Well, you do more and you submit again, right? And hopefully there will be some smart people who get accepted, if you're lucky. I hope those smart people remain, and we're not on the hands of this AI stuff in the end, because I don't want AI reviewing my papers. I'd prefer a smart person who is harsh but fair reviewing the papers, as opposed to some, as opposed to something that doesn't have those characteristics, let's say, any of those. You need that combination, right? You need some critical eye, but very fair person, right? Humans may not have either, but AI may not have either as well. At least there are some humans that are both critical and fair, and those are the ones actually who push the boundaries. I think that's really important to have, and that's the kind of people that we should be educating. We want critical thinkers, we want fair people, so that they can realize when something comes in front of them, oh, this is golden, and things are done right. So we should really publish it right away. So that's the important thing. The good news is people are actually in a different mindset right now. I don't know what will happen if they actually get something that's also golden. But read disturbance is mainstream right now. There are a lot of sessions in HPCA, ASPLOS. These are top conference, ISCA, coming up at the Micro. And we organized this DRAMSec workshop with ISCA recently. You can watch the full workshop on YouTube. There's a panel session with a lot of industry folks. You can actually see what industry is discussing, which is also interesting. And there are also sessions in using security. This year is using security at 7 papers on RowHammer, which is fascinating, right? This is like 12 years after we published the first paper. There are still 7 papers on using security. One of them is on GPUs. The other, there are a couple of other interesting ones, which when we get to RowHammer, maybe we'll discuss it. But basically, we talked about technology scaling. We talked about multiple issues in technology scaling, and read disturbance is one technology scaling problem, and finding a good solution to read disturbance is difficult, already difficult, and will become more so because technology scaling is not on your side over here, right? It's actually making the problem much worse. Okay, this is a good place to take a break, unless there is a burning question. Okay, let's take a break until 50. Yeah, 14:50, and then we'll continue this lecture. Everything good? Okay, you can hear me. Okay, let's get started. So now we've covered an overview of scaling issues as part of the trends. And because of the scaling becoming very difficult, there's actually more innovation on the memory side, especially recently. We covered some of these things. And because it's difficult to significantly improve capacity and energy, people have been investigating emerging memory technologies, like different types of DRAM also, I would say. They're not necessarily emerging, but 3D stacked DRAM, for example, 3D stacking logic as well as memory layers together that enables new opportunities. But with 3D stacked DRAM like HBM, which is potentially fundamentally 3D stacked, even though it's not used that way, at least with the logic layer, but memory is 3D stacked today, you get higher bandwidth out of memory. There's reduced latency DRAM that we're going to look at later on. You get lower latency. Low power DRAM, you get low power clearly. And there's a lot of emerging technologies that happen to be non-volatile, because a lot of them are resistance based that we're going to cover, especially in the emerging memory technologies lecture. They give you a larger capacity and better cost, potentially, at least in the longer run, maybe not in the short term. So these things have been enabled partly, in good parts, because technology scaling has become very difficult, but also due to different demands from different applications. For example, 3D stacked DRAM, reduced latency DRAM, low power, different use cases, right? We're going to see some of these later on. The downside is there's always a downside, basically. There's no memory technology that's good at every single metric that we care about. These are some prevalent metrics. For example, 3D stacking, because you're stacking multiple things, multiple dies on top of each other. You're essentially creating a thermal bottleneck. You're limited by temperature over there, because heat cannot escape easily anymore because you have many dies on top of you or underneath you. And as a result, you cannot stack an infinite amount, let's say. As a result, you get smaller capacity, right? You get higher cost with reduced latency DRAM. We're going to look at that. This is a very fundamental trade-off, latency versus cost. And we discussed that when we talked about trends in the last lecture. Low power usually comes at the cost of more cost and higher latency. And yeah, larger capacity comes with different types of costs, depending on the technology. So basically, there's no single memory technology that's good at every single characteristic. It's good to think about that. Actually, if you took DDCA, Digital Design and Computer Architecture, from me, you have seen that we did a very similar analysis, a much more rigorous analysis, actually, for SRAM, DRAM, and PCM in that class in the Digital Design and Computer Architecture. And clearly, there are trade-offs in different memory technologies. So if a single memory technology is not good at everything, why don't we actually put together different memory technologies that are good at different things and that are hopefully bad at different things, and design the memory controller and the system such that you, as much as possible, exercise the good things of each technology while avoiding the bad things of each technology. That's the idea of hybrid or heterogeneous memory systems. And when I made the slide, like, I don't know, 10, 12 years ago, this was not exactly real. But today we have different types of DRAM, for example, right? We have some DRAM that's high capacity, high latency, low cost, and some other DRAM, HBM, let's say, that's low capacity, high bandwidth, high cost, high energy, etc. Right? If you think about it, these are hybrid memory systems. Maybe we're not using it as intelligently as we should today in GPUs, for example, or GPU type of systems. But fundamentally, you have hybrid technologies that are there in a single node today. So this is another example. You have something like DRAM that's very fast, relatively durable, but that is relatively small compared to a more scalable technology, let's say phase change memory. And that's leaky, that's volatile, that's probably high cost. Whereas phase change memory could be large, non-volatile, maybe lower cost, but it's also slow. It wears out. It has high energy, high active energy at least. It doesn't have refresh because it's non-volatile. So that energy goes away, but active energy is actually higher as we will see in the emerging memory technology sector. So it's just one example. You can also have multiple different types of DRAM. You can have 3 or 4 or 5 different types of memories. And now if you have this sort of main memory, this becomes more scalable also, right? Because now you're not dependent on a single technology. If you're dependent only on DRAM, if it has scalability problems, then you're dependent on that only. But if you have 2 different or 3 different technologies that are hanging off your node, then you can try to intelligently manage them such that you can have a much better technology scaling landscape because you're not dependent on a single technology. Okay. Basically, the question over here is how do you manage these memories? And we're going to see that when we talk about emerging memory technologies. And you can manage them in hardware using memory controllers. You can manage them in software. You can manage them in both hardware and software. And you can manage the data allocation and movement such that you can achieve the best of each technology as much as possible. So to be able to do that, of course, your hardware and software needs to be aware of different types of technologies. And that's the idea over here. And this also requires some intelligent controllers, by the way, because you usually, if you just manage them in software, it's too slow. You're not really taking advantage of the technology as well. For example, you have some hot data and you want it to be in the fast memory as much as possible. Software may not be able to identify that quickly and move it to the fast memory. But hardware may be able to identify that much more quickly because of the access patterns that it can monitor. And it can move the data from the slow memory to fast memory, like phase change memory to DRAM, relatively quickly. And for that, you need an intelligent controller, essentially. So this is another reason why we actually want intelligence in the controller so that we can manage this sort of hybrid memory technologies. But this is a major trend that's actually real today. In my opinion, there will be more and more of these technologies that are going to be hybrid. And people have been also trying to, for example, use DRAM or different types of DRAM plus flash as a memory extension. So flash memory could be your main memory extension, which is essentially another technology that you take advantage of as part of your main memory. Okay. I should also say that this is an area where industry has been writing papers about it too. This is another paper that I would recommend in addition to that SK Hynix paper that I mentioned. This is a relatively early paper. This is in 2014. There were some forward-looking people at Samsung and Intel who got together and wrote a paper. We organized a workshop, actually, I don't remember, the memory forum at ISCA in 2014. And we invited them to write this paper. And they were actually very positive in writing this paper. These are folks from the DRAM design team at the time at Samsung and some memory controller plus DRAM folks at Intel. They got together and they said, basically, we're having a lot of problems with memory technology scaling, DRAM specifically, and we need to solve them. And the solution to them is not easy at the technology level. You can see that refresh is one problem. Write latency is one problem because as you reduce the size of the cell and also the structures, it turns out there are some resistance issues that you have, and that increase the write latency. And variable retention time, you're going to get to know a lot where the retention time changes randomly. They did not talk about RowHammer because we wrote the paper in the same, let's say, conference at the same time, but RowHammer can be easily added to here. But essentially, they said that solving these problems at the device level and the circuit level is very challenging. So we really need to rethink the controllers to solve the problem. So co-design the controllers and the DRAM. This is very similar to what we had been arguing at that time. And these folks actually looked at some of our works that we will discuss later on, sub-array level parallelism, and they evaluated completely independently and saw that there were a lot of benefits at the system level to implement them. And that's one of the reasons why they wrote this paper, to try to get it into the standard. Okay, so it's good that industry, at least the forward-looking people in industry, are thinking about this and writing papers. Industry in general doesn't want to write papers, but they do write papers once in a while. And this is another paper that we just discussed from SK Hynix, more recent, which I'm going to skip. There are also other papers. It's a very hard to read paper from Samsung. And there are also other people, like people who don't manufacture DRAM, like Microsoft, that are writing papers in this area. And this is actually one of the solutions, like per row activation counter, kind of grew out of the solution from Microsoft. And as a result, it was standardized overall over time. Okay. And you know that there may be downsides, of course, to all of the solutions. So it's good to keep that in mind. A solution coming from, regardless of where it comes from, you need to critically analyze it and scientifically investigate it, basically. Okay. So I'll cover one more issue as something that we're going to cover even later, or I don't know, actually, somewhere in the middle, somewhere before emerging technologies, unless we reorganize some of the lectures in the course. And this is a very fundamental issue also. So it doesn't matter what technology you implement main memory with. It doesn't matter what kind of core, accelerator, etc. you have on the processing side. As long as main memory is or some sort of memory is a shared medium for different type of compute units, you have some sort of interference problem. Meaning these cores, in this particular case, need to access main memory, and there is some path they need to go through to send their address requests, commands, and to get their data. That means, and that's a shared medium, and they don't have individual paths to the main memory. That means they interfere with each other when accessing shared memory. And if you don't control this, if you're not careful about who to give access when, then this may lead to a lot of problems, like quality of service, performance, predictable performance, fairness. So there are a lot of issues. This is essentially a shared resource. You have a shared resource in main memory. And how do you control access to that shared resource? How do you partition that resource in terms of capacity, bandwidth? Do you provide latency guarantees? Do you provide bandwidth guarantees? These are actually very interesting questions. Not easy to solve. And this problem is becoming more complex, basically. So you have many different types of accelerators. This paper doesn't do justice, actually, but it's kind of my cartoonish picture. Let's say you have general purpose cores. They could be small or big. You have GPUs, small or big. You have hardware accelerators, different types, video encoding, decoding, for example, audio. More and more machine learning accelerators that are more specialized for the task. It could be a vision accelerator, for example, especially in an SoC for different use cases. You can have a lot of these different compute units. And usually they share some parts of the hierarchy for resource. They share some resources. And almost always they share the main memory, because main memory is expensive in terms of bandwidth because you go off chip. And if you don't share it, you need to have a lot of pins, and that's extremely costly. So this sharing across different units causes clear main memory interference between these different types of accelerators. They could be executing different types of programs, right? Some of them may have latency requirements. Some of them may have bandwidth requirements. Some of them may not have any requirements. They could be okay with executing whenever, right? So it's good to think about that, right? The question, of course, becomes like, how do you allocate these memory resources to these heterogeneous agents? And how do you mitigate interference? And how do you provide predictable performance when for the applications that need it? And this is a very fundamental problem that people have tried to tackle. And we're going to see some solutions to it in later parts of the course. So clearly there are some examples that I'm not going to go through right now, but CPU, GPU, for example, if you have a CPU and GPU on the same system, which you need for accelerating different types of workloads. And if they actually are executing parts of the same workload or different workloads, or a combination of that, actually, how do you actually do the scheduling on the memory side? Not an easy problem. And this heterogeneity becomes even worse if you actually have many accelerators. And this is one work that we may cover later on. And then there's also predictable performance, which is, can you enable predictable performance for different applications? I'm going to skip these. This is just a flash because we're going to cover this memory interference, quality of service later on. We're going to look at different approaches to doing this. It's not just scheduling in the memory system, but it's also, can you partition things at the operating system level, for example, such that you reduce the interference across applications. We're going to see different approaches to this problem, but this is just to get you thinking. So predictable performance is usually a tough thing to enable. So basically, we're going to look at a lot into memory control, both at the hardware and the software levels. And these will actually become more important because so we clearly don't have a problem with adding more cores to the system. That's because people are adding more cores. We clearly don't have a problem with adding caches, but we have a big problem supplying those cores and caches with data from main memory and controlling that main memory. So that's really the bottleneck, as we have discussed earlier. And that's one of the reasons why memory controllers are going to be more important. So if you think about it, everything goes through the memory controller. If you want to, for example, this core wants to access some data from main memory, it goes through the memory controller. This GPU also goes through the memory controller. When you want to transfer data from storage to main memory, that goes to the memory controller. Your storage SSD is connected to your main memory through the memory controller, essentially. So there's a contention over there. Network, when you actually get data from the network, where do you bring the data? Goes to the memory controller in general. People have actually proposed directly putting the data into your caches, but your caches are in general not enough. Very hard to manage that one. So it goes through the memory controller. But you could also optimize things to go through caches sometimes. So memory controller is actually really the center of where the data moves. Almost everything in a system goes to the memory controller before it gets processed. That's why it's going to be more important to analyze them. Okay, this also means that we need to have better ideas in general. And one of the things that we will examine in this course is how to more, let's say, design systems in a more easier to design way, I should say. More, I don't want to call it necessarily more principled, but maybe it's more principled also. Can we somehow take advantage of, for example, the multidimensionality of some machine learning algorithms that they bring that are sometimes difficult to do as humans, and use these machine learning algorithms inside the design of a memory controller, for example, or a prefetching engine. So we're going to cover some works in this direction also, and I like this direction. This is a direction that we had worked on in the past. This is a paper from ISCA 2008, where we applied the reinforcement learning principles to memory controller design. And I think memory controller is a very hard part of an existing system to design. And if you can actually ease the design of the scheduling algorithm by taking advantage of machine learning principles, that could be very useful. And when we have time, we can discuss where else in the system these principles may be applicable. This is actually a very hot area right now. It was not an area in 2008, but right now people call it ML for systems. There's even a conference for this, ML-Sys, machine learning for system design. And I think this is one example of the approach, using machine learning to design a better system. Not necessarily optimize the system, but also make decisions in the system. Can I actually have a controller that uses reinforcement learning principles to decide what request to schedule next? Right? That's the idea over here. And that's very interesting because these are very hard things to design. If you can actually do this, maybe the controller can discover something that is not possible to do as a human, because humans cannot really think of more than a few dimensions, right? When you're doing memory controller, as we will see later on, there are so many things to think about. It's very difficult to actually do something that's sophisticated, because as a human, it's just not possible to actually keep everything in mind, right? It's fun to think about. Sometimes you need to design these things to actually know how to design these things. My favorite story about memory controller, maybe I should bring it here because it's a high level thing that we should talk about. Like complexity of design is becoming very difficult. The question is, what are the parts of the design that are really complex, and we should eliminate the complexity. When I was doing a lot of research on memory controllers, I was at Microsoft Research. We started area of memory controller design. At the same time, there was a person called Chuck Tacker, who was also at Microsoft Research, very senior person. How many people know that name? Chuck Tacker. Okay, only one? And you were the TA for the course. I'm not going to put more people on the spot, but it's good that you know. How do you know the name? Okay, last year's computer architecture. He took the course last year. Yeah, Chuck Tacker is a Turing Award winner in 2017. He's an industry veteran. He actually designed a lot of early personal computing systems, like Xerox Alto machine. How many people know about the Xerox Alto machine? Not many people. So before your time. Don't ask ChatGPT. go read the real history, because ChatGPT may not give you the wrong answer. But basically, there was a time when people were designing personal computers in the 1970s. And clearly at that time, there were no personal computers. These people were pioneers in the area. And they actually needed to solve a lot of early problems that not many people have seen. And Chuck Tacker was one of the key architects of this system, including the operating system, virtual machine, etc., and the hardware. And at Microsoft, when I was there in 2006, 7, 8 or so, 9, basically he was designing these memory controllers. He decided he was interested in FPGAs, designing FPGAs, and he wanted to design a DDR3 memory controller at the time. And he was not happy. Basically, we discussed, because I was also working on memory controllers a lot at the time. And he basically said, I designed a lot of systems in my life, and this is the worst thing, most difficult thing that I have ever had to deal with, the memory controller. So this gives you an idea, right? And I kind of agree with him, actually. It's very difficult to design modern memory controllers, both at the hardware level to get them work at very high frequencies. This is one of the most difficult mixed signal analog design circuitry that we have today because of the frequencies that we're dealing with, but also at the algorithm level, hardware algorithm level. How do we actually schedule requests? How do we actually design the scheduler so that we actually make the right decisions in terms of performance? How do you schedule refreshes, for example? A lot of those things, yeah. So I think that's a very difficult part to design. So machine learning can actually aid here. Okay. So I gave you some examples. No questions. Then I'm going to give you some broad strokes that we're going to cover. Basically, the question is, how do we solve the memory problem? Clearly, we have a memory problem, and we're going to cover a lot of solution directions starting maybe today, maybe tomorrow. Let's see. I think there are multiple directions that we're going to examine. One is making memory and controllers more intelligent. And clearly, I've given you some examples of this, but it's not just intelligent controllers, actually. It's more than that. Intelligent controllers are a part of it, but we also want new interfaces to memory, maybe new functions in memory. Can we actually do more things on the memory side? And maybe new architectures in memory. And then also we want the system memory co-design so that we can enable these solutions in a nice way. This will become more clear, but we want to re-examine how we actually think about memory and how do we actually access memory and how do we do computation in memory. We're going to look at a lot of examples of this, but this is one solution direction. Another solution direction is replace bad technologies with good technologies. That's what I call over here. Replace or eliminate this problem basically somehow. The difficulty is there's no technology that's good at everything. And this is going to come up over and over. But new technologies can enable a different way of thinking in the system. That's the benefit of different technologies, in my opinion. Sometimes you get these car salesmen who act as memory salesmen, meaning I've seen many times in industry where someone wants to raise money, and what they do is they basically say, oh, I came up with this memory technology, and this is better than sliced bread, meaning it's good at every single metric. Whenever you see that person, run away. I'm just kidding. But basically question them. Let's see. Let's start with metrics. And this has happened, for example, in STT-RAM, spin transfer torque, a magnetic memory. Whenever it was introduced in 2010 or so, especially the hype of it, people were selling it as the memory technology that will replace SRAM, DRAM, flash. Okay, it's good to ask questions, right? How does this work? What is the different metrics? So it's good to, that's why I said car salesman, because car salesmen have a very specific way of selling cars to you. But it doesn't work very well in memory. Clearly that STT-RAM didn't work. We did a lot of work on STT-RAM, by the way. But essentially, eliminating is very difficult. Coming up with a memory technology it's also called universal memory sometimes, universally good at every single metric, is a worthwhile problem to try to solve, but it's a very difficult problem to solve. Usually, if you come out with a new memory technology, that's good. It's good to understand its properties. Like what is the latency characteristics? What is the endurance characteristics? What are the robustness, different types of robustness characteristics, etc. How does this thing scale, etc. And in general, it's always a trade-off. You always have some positives and negatives in terms of the metrics. But this is a good thing also if you examine these emerging memory technologies that can enable new functions, and maybe you can rethink the system, assuming they're successful. So we're going to look at the emerging memory technologies aspect of it as well. And also we're going to look at different types of DRAM like HBM, 3D stacking. 3D stacking was an emerging memory technology when I first started teaching this course, and we actually looked a lot into it. But today it's actually, in my opinion, emerged, but it has more room to cover. Okay, the other solution direction is actually, if you have some problems, maybe you embrace your problems and deal with them in a different way. Right? I like this idea also. So maybe none of your technologies are perfect, and you cannot get rid of the problems easily. Why not take advantage of the downsides of a technology? Maybe use that as a feature as opposed to a bug, right? So here, for example, we're going to see some techniques. I'm going to actually mention them soon. You can design heterogeneous memories, none of which are perfect, but you understand the characteristics of your data and application and map data intelligently across those heterogeneous technologies such that you don't run into, let's say, security problems, or you satisfy your performance requirements. And this could actually enable new models for data management and maybe usage of technology. So I think there's a lot of potential over here. And maybe there are other solution directions over here. Let's see. So in the end, I think what we're not going to be easily escaping from is solutions will need to be across the stack in some way. You need cooperation between hardware, software, sometimes devices. And you need exposure at different levels to the lower level, essentially. So we're going to cover a lot of these solutions. So hopefully it'll be interesting. So let me quickly go over some, again, broadly. We're going to look at memory-centric system design a lot. We're going to try to overcome memory shortcomings. We're going to look at novel memory architectures, new interface, new functions. We're going to hopefully look at better waste management because there's a lot of waste in memory. We're wasting a lot of latency. We're waiting unnecessarily. We're wasting a lot of bandwidth because we're bringing a lot of data when we're not going to reuse a lot of that data. We're also wasting a lot of storage because maybe we can compress a lot of that data, right? So these are all examples of waste. And there are many issues over here that we're going to look at. We're going to start with enabling computation close to data, memory-centric computing. But we're going to look at robustness. We're going to look at energy, latency, bandwidth, and reducing waste. So there are a lot of interesting things. And this slide is some of our work in this area that I stopped updating some number of years ago. So there's a lot more work in this area, as you can see. The other direction that we're going to look at is emerging memory technologies, like some emerging memory technologies that seem more scalable than DRAM, for example. These are resistive memory technologies, and they're non-volatile. Phase change memory is one example. Let me give you very quickly what's coming. Essentially, in phase change memory, the fundamental operational principle is different from DRAM. It's not charge-based. You store data by changing the phase of a material. Basically, phase affects the resistance. And the material in nature exists in two phases, amorphous and crystalline. Material can be multiple different types of material. It could be glass type of material, for example. And you basically induce a phase change. That's why it's called phase change memory, to store a 0 or 1. And one phase is high resistance, the other phase is low resistance, essentially. And the fact that the ability to reliably change the phase of the material enables different types of storage. Everything okay? Okay, you can hear me, right? Okay, good. Okay. And this was expected to scale to much smaller nanometers than DRAM, at least earlier. And it was prototyped at smaller nanometers than DRAM a long time before DRAM came to 20 nanometers. It's a beautiful paper, IBM, in 2008, as you can see. And you can also store multiple bits per cell, which is a concept that we will see when we get to flash memory, for example. So essentially, it could be much denser than DRAM and much more cost efficient because it can scale to much smaller nanometers, assuming you can fabricate it at low cost, let's say. But that's the assumption. Whenever you go into emerging technology, you don't expect it to be low cost overnight, right? That's an unreasonable expectation, right? The DRAM technology didn't become low cost overnight. It took it at least 10 to 20 years to become low cost over time, right? So you need to make the investment to enable a new technology. And if you don't make that investment, new technology will never be enabled, and then you're stuck with old technology. There's also another thing about innovators' dilemma, right? If you don't invest into new technology, you're stuck in old technology and you do business as usual. But usually, in general, people who advance technology and science take the bold steps. They basically say, "Oh, I'm going to make this investment. I'm not sure if it's going to pan out. It's expensive, but I'm going to do it because there's potential," right? That sort of thinking needs to be done much more going into the future if you want to solve big problems. But anyway, you can store multiple bits per cell because you can chop up the resistance range into smaller ranges. For example, if your resistance range is from 0 to 100 farads, you can divide that into levels of four ranges, 0 to 25 and code 0, 0. 25 to 26 to 50 encodes 0, 1. 51 to 75 encodes 1, 0, and the remaining part encodes 1, 1. Now you encoded 2 bits of data across that range. Okay, so that's the idea over here. Now the issue is, and this is one example emerging memory technology. There may be other emerging technologies like STT-MRAM that we kind of had fun with earlier. But emerging memory technologies in general have shortcomings. Some of them have many shortcomings to begin with, especially. The key question is, can we somehow enable them in the system? Can they replace some technology? DRAM is one example. It could be flash also. Can they augment that technology? Can they surpass that technology? These are very good questions to ask, critical questions, basically. And that's the beauty of architecture, I think. People can imagine things, right? As an architect, for example, I may not actually know exactly how this technology will work. But as an architect, I have to do these studies to understand if it works, these are the characteristics that I want from this technology. And that could actually enable the development of the technology in a better way. Right? Or if the technology has the current characteristics that I think it has, here's what it will buy us. As an architect, you can make these decisions. And it's very important to make these trade-offs. It's important to make these studies so that you can actually enable a technology, enable a system that uses a technology. So we've done this, and we're going to cover some of these in our works. And phase change technology was very, very interesting. It was so interesting that eventually Intel productized it. They fabricated it. This was real memory that you could buy. Maybe you could still buy it. I don't know. If you go to Amazon or somewhere, maybe you can still buy this DIMM. But unfortunately, they stopped developing it because of costs, and Intel has a lot of issues these days beyond just manufacturing this. So who knows why? But in my opinion, this was actually a very good direction in the investigation of emerging technology. And I give Intel a lot of credit for that. I think Intel was mismanaged very badly, especially in recent years. But they actually was a very innovative company until maybe the non-technical people started taking over. Intel was a very technical company, you know. It was actually founded by engineers and very smart ones. And they actually set the course of the company such that it was built on innovation. And this is one of the example innovations that they actually put into the market. Has anyone used this? Okay. Can anyone buy it? Did anyone check? Probably you can buy it for a lot of money these days because it's not in production anymore. But this is actually phase change memory-based main memory technology. You can replace in your DIMM slot. You can put it in your DIMM slots, and it can be your main memory can be non-volatile. Very different from DRAM in that sense. It's actually quite dense also. It was not terribly expensive either, and you can see that the stick is actually pretty large, 128 gigabytes. Anyway, so basically. Some of these ideas actually can be realized with a lot of work, of course, at different levels of the stack. But these architectural studies are actually critical to enable that sort of, or to show that this actually could be very useful at the system level. There's, of course, a lot goes into the fabrication of this. And fabrication challenges are costly. Like it's very difficult to replace existing technologies because of this. But this doesn't mean that people should not be investigating new technologies. Okay, so we'll cover some emerging memory technologies also. And we'll cover the hybrid memory systems combination that I've already mentioned. Okay, let me give you another example, a different way of thinking. This is the embracing part. So if you actually have hybrid memory systems, and if you understand your applications and data characteristics really well, you can take advantage of different types of memories. So this is one way of doing that. There are other ways that I will also mention. So for example, you know that some part of your application has a huge vulnerability to errors. If you actually get a bit flip, your application crashes, or say you have security issues, etc. You want to protect that, right, as much as possible. But then there are some other parts of the application, if you get a bit flip, you don't care, because that flip doesn't affect the important part of the logic of the application, let's say. It doesn't get exposed to the user. If you can somehow characterize this in your application as you have vulnerable data and tolerant data to errors, you can design different types of memories or customize existing memories that work nicely with this sort of data. Clearly, vulnerable data should go to reliable and secure, robust memory. And tolerant data, maybe it can go to low-cost memory that is not as well tested. So there's a design space over here. We call this heterogeneous reliability memory. With Microsoft, we did studies on important applications like web search. Web search is a very nice one. that fits this. There are some critical parts of web search that are important, but there are some non-critical parts also. Who goes to, for example, the third page on Google? Not many people. Maybe they're not as critical, right? Ordering over there doesn't matter as much, right? But the top page, the ordering may matter quite a bit, right? So that's one of the ideas, right? So that ordering logic, depending on where you are, may have a lot of importance or no importance, and you can take advantage of that by mapping your data in a careful way across different memories. So basically, you can have reliable memory that's costly. It could be protected with high levels of error correcting codes, for example, and low-cost memory that's low cost. Essentially, it's not protected as much. But then you map your data intelligently such that important data doesn't go to the low-cost memory. Important data goes to the protected memory. That's the idea. This is a general idea. And we actually did a lot of studies, again, with Microsoft, and we showed that this works reasonably well. You can actually reduce server hardware costs. Instead of protecting all of your memory with expensive error correcting codes, you can reduce server hardware cost. In this case, it wasn't even expensive error correcting codes. If you remove even the cheap error correcting codes, you get benefit, as you can see, in terms of hardware cost. And you can still achieve a good availability target. Okay, this is the idea, basically. It's a cross-stack idea. Generalized, you have a lot of applications, a lot of data. You somehow characterize them and classify application memory error tolerance. And then there is a continuum of different types of data, vulnerable and tolerant. And then you map the application data to this heterogeneous reliability memory with some software hardware changes. So this requires you to classify data and also map. So this requires both hardware and software changes, as you can see, right? Again, the paper has more details, and when the time comes to emerging memory technology, we're going to cover this more. And there are some cases where this makes sense, some applications where this makes sense. And again, I will not go through that right now because it's an introductory lecture to see the broad strokes of what you can do. For example, and there, again, it's always good to evaluate many different metrics. So for example, how many crashes do you get because you're not careful? What is the cost savings you get? What are the incorrect queries you get? How important they are? What is the availability of the server? And what is the hardware cost savings that you have in the server hardware in general? And if you look at this, I think we make the argument in the paper that this heterogeneous memory with less tested chips actually achieves a good balance over here compared to a typical server. Typical server is actually very costly, whereas you get a lot more cost savings while not reducing availability and not adding at least too many incorrect queries in critical parts of the application. Okay. Okay, that's one of the papers. Like these type of ideas are actually really important to both evaluate and develop. Right? These are like when we developed this idea, this was a, let's say, relatively new thing, and I think there's more to be done in this area. And this is really an example of our axiom that we covered. Actually, this is really taking the expanded view of computer architecture. Right? How do you classify the data? How do you figure out its error tolerance? Right? Clearly, people need to be involved in it, right? It's because there are semantic characteristics over here that may be not possible to discover without humans in the loop. Yes? You mean this side of works? You mean this heterogeneous reliability memory? Or yeah, yeah. Yeah. I mean, so okay, that's a very good question, and there's no single answer, right? Because these things don't necessarily work in a scientific way. Something can be a technically great idea. It may not be executed well. That's one thing. Or it may not have the right cost point at that point. It may not have good enough applications. It may not have the ecosystem that's developed. I think in phase change memory, for example, one of the problems was it was not very open, right? It could have been much more open in terms of engagement with many people. If people actually were given the chance to develop applications for it as early as possible by enabling a much more open ecosystem, it would have been much better, in my opinion. It was mainly limited to Intel systems, for example, and that doesn't help. Right? Yeah. Change the business model? That's very difficult. You cannot do that as a researcher. But I think you can certainly do very open research, right? If you want your ideas to be enabled or adopted more easily, open sourcing your contributions. That's a very big first step, right? Because you open source your systems are complex today. People don't have enough time. If you actually open source your idea, other people can test it, and other people can adopt different things, right? So that's one step, I would say. The other step is, as much as possible, working with industry, people with the right mindset, right? Because sometimes you may do all the right things as a researcher, but the transfer actually happens with people transfer, if you know what I mean. So people who do the research go to industry and they implement the ideas over there and they convince people internally. So that people transfer is also important. So for example, when I interact with industry, I tell them, if you're interested in innovating in this direction, you should hire this student, right? Because that's the that's the way you can actually immediately boost how you can actually innovate, right? And from the student's perspective, also the same thing from the researcher's perspective. If you want to have a strong impact on industry, consider joining them for some time. Short time, long time, I don't know. I tend to do short time, for example, with industry sometimes, but I've been in industry in the past also for a longer time also. So that sort of people transfer also enables technology transfer. Okay. 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 DRAM, you said DIM interface, essentially DDR interface. Yeah. I mean, for example, so yes, we'll talk about that later. Yeah, let's discuss that. But SMD is, for example, a small step toward that direction. It doesn't fundamentally change the DDR interface. But I think the question is like, what part of the DDR interface is problematic? Let's talk about that when we get to the DRAM lectures in more detail, right? Because I agree, there are multiple different issues with the DDR interface. It's too detailed, let's say. But I think the upside, let's say, is too coupled to the memory controller. That's one of the downsides. But if you want to design a specialized circuitry that provides very high bandwidth, there are benefits to the DDR interface also. But we can discuss it when we get to it. Yeah. Okay, very good. It's good that people are asking questions. Okay, let's see. Okay, we talked about HRM. That's an example. Let me give you another example. This is also customizing memory to the different types of data that you have in neural networks in this particular case. Again, this is an example from our own work. And clearly, deep neural networks are popular. They're also expensive, especially for large networks. And we're going to see more and more of this later on. And in this work, the idea is very similar to HRM in a sense, right? You identify the data and layers in deep neural networks that are very tolerant to errors. And you can quantify this. And you can map this data and layers to low energy, low latency DRAM that may have errors. As long as you can tolerate those errors, right? Maybe your accuracy is still good enough, right? If you do this sort of mapping, while still achieving a user-specified accuracy target. And you can actually achieve this target by training your neural network in a different way, such that it's aware of these errors that are induced by, let's say, a low latency, low energy DRAM. That's the idea. This is a high-level idea again. So this is an example of data-aware management of DRAM latency and voltage for a specific domain, deep neural network inference. You can apply it to other domains also. Let me give you an idea. These are real results from a neural network, ResNet, relatively old one, but you can apply it to newer ones also. You can basically do studies to identify which layers of a network. This is a 50-layer network. You can look at every layer's weights and input feature maps. And you can figure out which layer can tolerate what bit error rate to achieve a particular accuracy target. If you can do this classification in a nice way, such that your results are trustworthy, now you can identify, okay, layer 0 can tolerate, for the input feature maps, inputs to that layer, can tolerate maximum 2% error rate. And layer 1 can tolerate this much, and then you can sort the layers based on how much it can tolerate, right? That's the idea over here. And then you can actually design your DRAM. You can map your error-tolerant DNN layers to memory partitions with lower voltage and latency that match that error rate. That's one idea, right? So for example, you may have 4 partitions with different error rates. You map these not so tolerant layers to a strong partition, let's say, that can give you less than 2% bit error rate. If you need even stronger, you make it as you make it even more expensive. And you map these other layers over here to, because they're more tolerant, to another partition that gives you a guarantee for less than 5% bit error rate. And then like this, yeah, you get the idea, hopefully. So you match the bit error rate requirements of the application or pieces of the application to the bit error rate guarantees of different partitions of memory. Of course, in order to be able to do this, you need to know your application and you need to know your memory. If either of them cannot guarantee, if either of these is wrong, then you're in trouble, right? You may think a layer can tolerate 8%, but it can actually tolerate less than 1%, then you're in trouble, right? Because you may map it somewhere that has a lot of errors. So that's why this is important. This is hardware-software co-design. It requires a good understanding of your application and profiling of it, as long as you do the right thing with the right data sets that you're going to actually see in the system. It also requires you to correctly identify your hardware, because if your hardware promises that it's not going to get more than 2% bit error rate, but it actually gets 5%, then you're getting in trouble, right? So that's the danger of this sort of hardware-software co-designs. You need to be much more careful because you're really trying to match it to the match the software behavior to the hardware behavior. But it's good to examine this sort of ideas. And again, we're not going to cover this work in detail right now. This is just to give you an example of these data-aware mechanisms, as we call them. Essentially, what you can do is, after you do the mapping of your DNN to DRAM, what you can do is you can simulate, you can profile what happens. And if you haven't reached your accuracy target, what you can boost your error tolerance. You can retrain the network, essentially, with those in mind. So this is called error-aware training. This is not the first work to do this. There are many other works that look at that. So you can actually change the weights, etc., and in the neural network to match the error profiles that you get. Okay. And in the end, you can actually get good energy reductions and performance improvements. And you can read the paper for more detail. In the paper, we evaluate GPUs and also machine learning accelerators at the time, TPUs. But this is another example of how innovative you can get, right? It's not easy to adopt this sort of thing immediately. It requires change to the hardware and the software. But it's important to investigate because it's really a cross-layer approach that can make your system a lot more efficient. And there are many other works that came after this that talk about something similar. Okay, I'm getting closer to the end. But this is an example of a data-aware architecture. I'm going to skip the slide because we're going to see the slide later on. But what is a data-aware architecture? Like, this is really an architecture that understands what it can do with and to each piece of data. So in this particular case, in the example that I gave you, we understand the error characteristics of the data, different types of data. And based on those error characteristics, we map the data to a particular piece of hardware that matches the error characteristics. That's a data-aware architecture. A more accurate way of describing it, probably data characteristic aware architecture, right? But that's data characteristic aware is a bit mouthful. So I call it data aware. And this architecture can make use of different properties of data to improve different metrics: performance, efficiency, robustness. And there are many data characteristics that are there. How compressible your data is, for example. What kind of algorithms can it be compressed with? If you know that information, if you classify your data that way, maybe in hardware or software, you can compress it in different ways, right? So you can actually have different compression algorithms built into hardware. Approximability is similar to what we just discussed, error tolerance. Locality, if you understand the locality characteristics of your data, you can map it to different types of memory hierarchies, for example. For example, you know that you're not going to get any locality in this part of the data structure that you're dealing with in your program. you figure that out either as a programmer or through the compiler. You map it to a memory hierarchy that bypasses all of the caches, right? Because caches are useless in that sort of system, in that sort of data. You understand the sparsity characteristics, criticality, meaning how critical is this piece of code for the application performance. If you know that, again, what you can do is you can, for example, map it to a very fast processor, right? So because this is really the critical path of the program, if you can identify that. So there are many, many things like this that are interesting, I think. And this sort of information is not exploited as much. And in this course, again, I would like to take a critical view of how we communicate information from the software to the hardware, right? If you think about like these characters, I'm sure if you think about it, you'll come up with 10 more characteristics like this. Then the question becomes, how do we treat all of these different characteristics in our hardware architecture today? And normally what we do is we don't take into account any of these. This information doesn't even get discovered or communicated to the hardware architecture. And we're going to see some approaches where we try to discover this information in some way, or the programmer needs to provide that information. And we design the hardware architecture to match different types of behavior of data. So this is a picture over here. Basically, what we do in many general purpose systems, and also many special purpose systems, although special purpose systems are a little bit better by nature because they're special purpose. You customize it for an application. That doesn't mean that you're customizing for all characteristics of an application, but at least they're a little bit better. What we do is we don't even know a lot of that information, or we don't communicate this information. So we have a hardware-software interface, especially in general purpose systems today, that's very limited. If you think about it, we communicate instructions. What should the instruction do? Add, multiply, divide. Maybe some data types, because those data types are actually encoded in the instruction. Every ISA has data types, but they may not match data types in the software. Software may have very high-level data structures, right? That maybe queues, graphs, right? That information is not necessarily represented in the hardware or communicate to the hardware. And you communicate memory addresses, but not much else, right? There's not much other information that gets communicated. So can we actually redesign an interface between the hardware and the software such that we communicate a whole lot more of this wealth of information about different characteristics of data and computation, such that underlying hardware, we can optimize the program much better. So this is one example over here. I think we need to do this more and more. This is a tough area, but it's an important area to look into. How do we actually design the interface such that we can provide higher level program semantics, data characteristics in a more expressive way to the underlying hardware, such that the hardware has choices to actually map the data in different ways, for example. So we actually have some work that I'm not going to go into in detail, but this is one of the works. Basically, software can provide key program information to hardware, like access patterns. I'm doing random access. I'm doing streaming access. I'm doing striding access with stride X, for example. Or data type, something simple, right? Or the compressibility of the data. And the hardware does this could be system software as well, by the way, but hardware or firmware does the data placement appropriately, such that random access requests are separate from the streaming access requests, because they can be handled much better if they go to different memory controllers, for example, right? It's good to think about it. So you can change the prefetcher, and this paper talks about some of them, which I'm not going to go into. You can decide the data compression algorithm that you use based on the higher level semantic information that you're getting from the software. So this is actually a very broad direction. Even though this paper does some specific things, the direction is quite broad, I think. So this way you can enable many cross-layer optimizations, right? There are a lot of things you can express. This, again, limited. And there are a lot of optimizations you can do in the hardware. And maybe you can get a lot more benefits this way. Okay, I will go through this relatively quickly because we don't have a lot of time. But how can you do this, essentially? The question is, how do you do this? I will not go into the details of this particular work, but this requires, again, thinking the software stack as well as the hardware. So you need to somehow provide some sort of abstraction from your program such that you can express the different characteristics of the data, for example. You need to be general, potentially, so that you can deal with different parts of the hardware. You need to minimize programmer effort. If you ask the programmer to specify how compressible is this data structure, they're going to look at you and say, I don't know, most programmers, because you don't want that to be programmers' burden. So you need to be careful over here. Overhead of keeping track of this information is also important. This may actually lead to. So if you want to, let's say, imagine you're dealing with terabytes of data. If you want to actually classify which data has what characteristics, it's a lot of metadata to keep track of, right? And if you're not careful about how to represent that metadata, it could be very expensive. That's one of the reasons why this is not done today, right? Because people don't want to represent this information. But if you can actually represent it with low overhead, it could be very beneficial. So basically, we want to flexibly associate semantic information with any data and code as much as possible. For that, you need to have some sort of interface. We call it expressive memory in this particular work, but I think the idea is much broader. And our goal, very quickly, is to convey data semantics to the hardware. And doing that enables more intelligent management of resources. And here we introduce a new hardware-software abstraction, essentially an interface in the ISA between the hardware and software. We call it Atom. It could be extended. But for example, there's an Atom associated. Oh, what happens here? There's an Atom associated with each memory region. And application specifies the characteristics of the memory region. In this particular memory regions can be of different sizes, of course. And for this memory region, for example, I have very good locality. I have very good compressibility. I have very good error tolerance. Or you can associate different memory regions with different atoms also. For this memory region, I have some other characteristics. For this memory region, I have some other characteristics. And then if this information is communicated, then the hardware or the system, both the low-level system software as well as the hardware, can take action on that region, right? If you think about it, this Eden work that I described is a special case of that, right? Special case of this expressive memory. Okay, so for this, you need actually some sort of interface. Again, this is a specific interface developed in this paper that describes, this is the atom that maps to this data structure. It's a regular access pattern, it's an integer, etc. So, okay, so this can enable a lot of optimizations. Again, this is a slide that's thrown at you from the paper, but if you look at it, what should I pick over here? Maybe cache and memory compression. For example, if you know the data types and data properties, if your data type is an integer, float, character, and your data properties, you have sparse data with some sort of sparsity, pointers, indices, you can use different compression algorithms for different types of data. Okay, it's good to think about it. This paper has some specific examples that I'm not going to talk about, but this sort of thinking is very disruptive in the sense that it's very difficult to get it adopted, right? Because you're changing the hardware, you're requesting a lot from the higher level software, and you're changing the interface. Essentially, you're changing everything in between. But this sort of thing is important to do because it's really important to explore what is a better interface that we can have, right? It's basically challenging the status quo. Someone designed this hardware-software interface. It's stuck around for a long time because people developed a lot of software on it. Why don't we question that, right? Why don't we actually try to make it better? So this is actually, industry has a lot of interest in this direction these days also. Like we did a lot of work with NVIDIA to look at how to express locality in a much better way. And I believe they're using some of these ideas in their recent GPUs. But basically, the idea is exploit data locality. And data locality affects a lot of things in a CPU as well as GPU. How do you place the data in different types of memory? If you have especially non-uniform memory access systems, for example, where do you put the data? How do you manage the cache? How do you schedule your warps in a GPU? And how do you do data prefetching, right? Again, if you know the locality characteristics of an application, you can manage a lot of those. And we have an interface, but I'm not going to go into the details of this. And if you actually communicate things nicely from the different data types or different data structures, objects, let's call them, and you can describe the locality characteristics of your objects, you can do much better of all of these, and you can get significant performance benefits. Again, according to this paper, that paper. Later, we also designed FPGA prototypes to see, can you do this in real hardware using, let's say, some toy processors, some RISC-V toy processors we had to deal with because there's no, let's say, big toy processor. Although these days there's they're very strong processors from Jiangshan, right? I think those are more interesting to examine than what we examined in this work. But when we examined that work was not around. Essentially, you want to also evaluate the overheads of this sort of metadata communication between the hardware and the software. It's not an easy area, but it's really important to do. Okay, we already discussed heterogeneous reliability, memory, Eden, etc. There's more that I'm not going to cover. These are all data-aware mechanisms. I think we may cover it at some point. We have the authors of this works somewhere, not here, but certainly in the group. They may present that. And virtual memory is something that we may also cover a lot because it's a tough area. So these are some papers on data-aware design that I'm not going to cover right now. Okay, let's see. Okay, that was just to give you an idea. Data-aware architecture is actually important. And now hopefully you know what I mean by data-aware. Actually, whenever you design an accelerator, fundamentally you become a little bit more data-aware compared to existing systems. But that's not what I'm exactly talking about, right? When you design an accelerator, you're really specializing the architecture to that accelerator. And clearly you're trying to specialize to the data types that are used by that application. So fundamentally, there's more data awareness. But even in that accelerator, you can distinguish between different characteristics, right? Yeah, so that's really important to think about. Okay. Okay, we're going some other things we're going to cover in this lecture is simulation. So you're going to do a lot of simulation, especially in the labs. But we're hopefully going to have a simulation lecture. So doing like real system prototypes is important. Doing studies with real chips is important. But equally important is simulating things that don't exist. And a lot of systems people are very uncomfortable with this. Even though simulation is a tool to do a lot of things, to discovery, for example. If you want to discover things in science, people do simulation, right? Molecular dynamics simulation, right? I don't know why software systems people are, let's say, not comfortable with this. Maybe they're not real scientists or something. I'm just kidding. But basically, I think people should be more comfortable with simulation in general, because if you want to discover something new, the system doesn't exist. What do? You either build the system, but maybe that's very difficult to do, especially if you rely on some technology that doesn't exist also. Then you got to simulate. But if you go to, let's say, some software systems conferences, oh, simulation, it's something that they don't understand, basically. But simulation is something that scientists do all the time, actually. They simulate cells, they simulate, I don't know, spread of diseases. They simulate a lot of things, actually. In the science, it's well accepted. Somehow the software systems or people who want to claim computer science for themselves, they basically say this is not accepted. But simulation is very important, actually. So we're going to look a lot into simulation. And developing simulators to enable the design of new systems is really critical also. That's why we developed a lot of simulators. We're going to cover some of them. Again, I'm going to flash these slides because we will have a simulation lecture. But doing simulation memory systems is really important. How do you actually enable a new memory technology or a different type of DRAM technology? How do you evaluate its benefits? You cannot design it. It's too costly. No one can fabricate it. Not just you. No one in the world can fabricate it. But can you actually try to understand what kind of benefits you would get with this technology? What solution do you have, right? You got to simulate. You're not going to be able to convince those people who cannot think beyond their, let's say, noses. But you're going to be convincing, or at least it's going to be interesting for people who really care about what is the importance of this new technology, right? That's why we designed RAMulator, for example. This is a very flexible simulator that enables investigation of many different types of DRAM technologies. And this is actually from 2015. This picture is from 2015. At the time, DRAM standards were bifurcating, meaning there were a lot of different types of standards that are coming up. And we wanted to design the simulator to actually investigate how these standards affect performance, energy, etc. Today, we have a newer version of it that I'm going to mention. But always, it's important to enable fast simulation, modular simulation, easy-to-use simulation, right? And these are some studies that you can do. This is, again, from our paper from 2015, where we showed that, for example, HBM is a good memory for especially workloads that need high bandwidth. Right? So you can actually do these studies, right, without building the system. And if you want to build every one of these systems to get this data, good luck. You're not going to be able to do that because even building one of these systems is very expensive. Now building, I don't know how many, 1, 2, 3, 4, 5, 6, 7, 8 of these systems plus one, which is the baseline DDR3, 9 of these systems is impossible, let's say. Okay, let's see. Okay, we're going to what some other things we're going to cover in this lecture is simulation. So you're going to do a lot of simulation, especially in the labs. And it's not just building those systems. You got to get exactly the same system, right? Meaning, if you want to do a scientific comparison, you need to control. Meaning everything other than the DRAM should be the same in the system, right? How do you get that to happen is another question. Here we do have that. Okay, that's the beauty of simulation, basically. It enables you to scientifically isolate things that you may not be able to isolate in a real system. Okay, so Ramulator 2 is there. You're going to do some studies with the Ramulator. Which lab is it? Do you remember? 4 or 5? Okay, 5. 5. Okay, cool. Okay, this is an optional assignment right now. You can review the paper right now. You can download and run it. This can help you get into memory systems research quickly if you're interested in this. Okay, this will be online. Okay, these are some of the studies that you can do with simulation, basically. We did a lot of studies, for example. This is from the original Ramulator paper. One of the things you can examine, for example, RowHammer solutions, right? We discussed RowHammer early on in this lecture. There are many solutions that you can develop and imagine. One solution that we developed early on is called Para, for example. Para is basically whenever you're closing a row in DRAM, you flip a coin. If the random number you generate is greater than some threshold, you refresh the adjacent rows to the row that you're closing. That's the idea. It's a probabilistic mitigation mechanism. Initially, it was a good idea. Right now, it's a tough idea to actually implement at low performance overhead. But still, you can examine these ideas. You can basically, with simulation, you can change the RowHammer threshold, meaning how many activations need to happen before a bit flip happens. And 10 means after 10 activations to a row, you get a bit flip, which is really terrible. That's a very low number. Today, we're probably around 1,000 or so, etc. So basically, you can check how these different solutions that people have proposed scale as RowHammer threshold reduces, as technology scales. So this is something that you cannot do with real systems. You have to really simulate. And this is how you can enable future research, basically. Because some solutions may or may not be scalable as you reduce the number of activations to induce a bit flip. For example, Para becomes not so good after some point, as you can see. This means people need to research better than Para techniques. In fact, we wrote that paper in 2020. It's called Revisiting RowHammer, and that enabled a lot of solutions to RowHammer that are much more scalable today than Para and some of the other techniques. So simulation is very, very beneficial, despite what some systems people may tell you. Okay, so this is another example where we evaluated the per row activation counting that is put into the standard with DDR5 and all upcoming DRAM chips. And basically, no, that should be count over there. Okay, I'll fix it later. But basically, here you can also see when a solution works, when a solution doesn't work. So for example, at RowHammer thresholds that are, let's say, greater than 64, greater than 64, maybe greater than 256, the solution that's proposed by industry, if it's configured accurately, is okay, maybe. But once we go into RowHammer thresholds that are really small, which is what the technology scaling is bringing us, maybe these solutions are actually pretty bad, as you can see. This is the normalized weighted speed up, essentially normalized performance. Ideally, you want to be at 1. You don't lose performance. But if you look over here, you lose a lot of performance with existing solutions. So this also shows that existing solutions by industry is not scalable. Okay, this is, and again, the only way to do this is by using simulation. Okay, so we'll cover a lot of things in the next several lectures. I will not go into that, but we'll start with computation and memory. That's that's going to be the major thing that we're going to look at in the next lecture, and probably the next lecture as well. And then we're going to cover a bunch of these issues. So we're going to cover a lot of memory to begin with. I will stop here. Are there any questions before we part? Okay, then tomorrow we're going to start with some techniques to do processing in and near memory. I call it processing in memory, but we're going to define also a taxonomy of processing in memory, because there are different approaches to it also. And hopefully we're going to cover a lot of approaches until the end of the lecture, and then we're going to continue next week. Okay, I'll see you tomorrow then.